All right. And I'm Beatrice. That's my name. I'll be your host for today's symposium. I've been an SEG active member for almost 5 years now, participating in the Unicamp SEG Student Chapter, where I served as president and as vice president. And I'm currently a member of the SEG Students Committee, which has been fantastic. I'm serving as South America student representative with Jose Moraga. That's my pair. And I was a fifth year undergrad geology student at Unicamp just until last week when I defended my thesis. So you have a brand new geologist here with you today. So very excited about that. And at the university, I worked as a teaching assistant for several courses, such as structural geology, economic geology, and I was a member of the Metallogeny and Crustal Evolution Research Group. And I also hold a degree in geography from the University of São Paulo, USP. And I'm currently a geology intern at the AngloGold Ashanti's Latam Geoscience team. And I worked before in two of their operations, the Córrego do Sítio and Cuiabá underground mines. So I'm very happy. I'm very happy to be here, and I'm very fond of sharing opportunity with other students and helping and engaging with their chapters worldwide. So please let me know if I'm able to support your chapter in any way, being a point of contact, especially here in the region. And I thank the Society for the invitation, and I'm very honored to be here. So there you go. And for those who may not be familiar with SEG, the Society of Economic Geologists is committed to advancing the science of geology through the scientific investigation of mineral deposits and mineral resources and the application to exploration, mineral resource appraisal, mining, and mining extraction, mineral extraction. So this includes the providing of world-class publications, workshops, webinars, such as this one in here, field trips, conferences, as well as developing the next generation of successful economic geologists. So we highly encourage anyone interested in our organization, especially students and early career professionals, to visit the Society web pages for more information. Yeah. Oh, I'm so sorry. Let me come back again here. Yeah, there we go. All right. And now it's a great time to renew and take advantage of all SEG has to offer. And feel free to scan the QR code and visit the segweb.org for more details and information. And personally, I can briefly share some outstanding opportunities that I had over the last couple of years. I would like to highlight the opportunity to attend the annual Ronald Seavoy student field trip that I took. That took me to Nevada in the US last year, where I visited several high and low sulfidation epithermal deposits there in Nevada, which was amazing. And there was also an opportunity to take the microfeatural mapping course just a couple months ago in New Mexico, learning several techniques while mapping up just a beautiful copper flat porphyry breccia system. And besides that, the chapter I'm from, we applied to the Student Wallace funding, and we also received funds to organize a field trip to Goiás State, where we drove over 5,000 kilometers and visiting six completely different type of deposits, mineral deposits, and collaborated with other student chapters from UERJ and USP in Rio de Janeiro and São Paulo. So there's much going on. There are so many opportunities to receive funds and presenting scientific work at the SEG conferences. And this year, the conference was in Namibia, Africa. It was fantastic. So yeah, besides geology, which is always exciting, the people we get a chance to meet during these experiences, oh my God, that's the best part for sure. I tend to get a little bit emotional when I talk about it, and there are several witnesses out there to confirm that to you. So I'll keep this short because I don't want to make you go through that as well. So, but that's it. Joining the society opened many doors to me, and it's been a game-changing experience for sure. And all that being said, I strongly recommend you to join us and apply to all these opportunities because receiving the funds and to do that was the only way I could ever do that at this point of my life. So for that, I'm so grateful to the society and to Dr. Chavez, an amazing person, Eric Peterson, Rolf Gonzalez, and all my SEG friends from many different countries. Well, I miss you. I always think about you, so please take care. And moving on here, and for those who are already members but looking to take your involvement, it's not working properly. Just a sec. Yes, sorry for that. Yeah, then. And so for those who are already members but looking to take your involvement to the next level, we highly encourage you to consider a fellowship. A fellowship allows experienced and passionate individuals to give back even more to the next generation of geoscientists, whether through greater involvement in mentorship, providing guidance and direction on society committees, or helping to foster growth in key development areas. So please visit the website page for more details. All right. So once again, thank you so much for joining us for today's event, the 2024 SEG Lecture Symposium. The SEG Lectures are globally recognized individuals that serve as ambassadors for the Society of Economic Geologists and who are excellent speakers selected each year based on their significant contribution to the field of economic geology. So the SEG Distinguished Lecture and Traveling Lecture programs provide support for lectures to present in person to SEG student chapters, universities, and mineral industry events around the world. And this symposium will continue that mission, but now in a virtual form. And today we are excited to host the SEG 2024 lectures for a series of great presentations and discussions. Here, let me briefly introduce you to our stars for the day. We have our distinguished lecturer, Adam Simon, our international exchange lecturer, Moira Smith, Thayer Lindsley visiting lecturer, Sarah Thayer, and our regional vice president lecturer, Raymond Seltmann. So I will welcome you all, and thank you so much for being here with us. That's our agenda. That's our agenda for today. We are starting now. We started right now at 11 a.m. Mountain Time, and we are trying to keep track on time because we have just a very global community in here. So let's try to do our best to keep on track on that. Here we were supposed to have Jennifer Craig. Unfortunately, she couldn't make it last minute, so we won't have her comments, unfortunately, right now. But then we are starting with Raymond Saltman. Then we are moving to the Q&A session. We have a Q&A session that lasts 10 minutes by the end of each presentation. Then we have Sarah with us, another Q&A session. We will have a very short coffee break, a 10-minute short break, just to stretch our legs. Then we have some summary comments from our President Steve, the SEG President. And then we have Moira's presentation followed by the Q&A, then Adam followed by another Q&A session. Then we are just wrapping up with Anne, our SEG President-elect for the next year. And then we are just wrapping things up and saying goodbye. Right, so our first speaker for the day is Reimar Seltmann. He's from the Natural History Museum. He's our SEG Regional Vice President Lecturer. And Reimar, I'll just introduce you, all right? And then I'll invite you to join us. So Reimar Seltmann joined the National Natural History Museum in 1999, and he's a research leader in ore deposits. And since 2002, he's the founder and head of CIRCAMS, the Center for Russia and Central Eurasian Mineral Deposit Studies. And Reimar served with his CIRCAMS team as key partner of the U.S. Geological Survey Global Mineral Resource Assessment Program, the GMREP, for Central Asia region, and is recognized by the international mine industry for leading geodynamic and metallogenic research and exploration services to the mining industry on the Altides region between Urals and Mongolia, Russia, and Afghanistan, with the CIRCAMS ArcGIS database and digital map of geology and mineral deposits of Kazakhstan and Central Asia as key product. And since 2021, he's an adjunct associate professor at Trinity College Dublin and visiting professor at the Ocean University China, Qingdao. And since 2023, he's also an honorary professor of the University of Geological Sciences in Tashkent, Uzbekistan. And Reimar has almost 40 years of experiences in studies of ore-bearing granitic system of Trans-Eurasian metallogenic belts, with a special interest in fluid saturation textures and magmatic hydrothermal transition processes of granite ore systems. And his mineral deposit research covers a wide range of mineral systems: gold, copper, uranium, rare earth elements, lithium, etc., with regional focus on geodynamic and metallogenic processes in ore district of accretionary and collisional belts. So Reimar's talk title is Critical Metal Potential of the Kazakhstan and Central Asia. And Reimar, I now invite you to join us. You may come on screen and turn on your camera. I can see you now. I'll drop my presentation so you can share yours. All right. Okay, it's done. Do my share screen whenever you're ready. Yeah, I can see your presentation. It's not in presentation mode yet. Oh, it's perfect. I can see it now. Thank you, Reimar. Thank you so much for being here.
Hey. Yeah, good morning, and good morning to US, and good morning in China. Here I'm live from Astana in Kazakhstan, relevant for my talk, Critical Metal Potential of Kazakhstan, Central Asia. In my cozy hotel room, outside is -20 and colder. So, and I will give you some excursion into Kazakhstan and Central Asia. So thanks for the introduction to Beatrice. And yeah, the agenda of my talk, I will speak about general aspects of what are critical metals. Then I will give you an introduction in Central Asia, geodynamic metallogenic framework as a commodity basket and the mineral potential with respect to critical metals. And I will introduce you to a few selected case studies of critical metals and give an outlook for mineral system approach aiding sustainable exploration. So, one of the first, or the first, critical mineral strategy was defined in the UK and was set out to secure UK's supply chain. And this, meanwhile, over the last 4 or 5 years, has been taken on board by many other countries and states, Canada, Tasmania, in Australia, various provinces, and Germany and other countries. So the UK's critical mineral strategy was a kind of role model for the others to accelerate growth of domestic capabilities, to protect the mineral potential and sustainable mining. And when we speak about strategic mineral potential, we have to understand or to divide what are critical minerals in contrast to other important minerals. Each country has its own definition relevant to strategic aspects. And critical minerals are not only vitally important, but also experiencing major risks to their security of supply. So critical raw materials, or CRMs, include or are a synonym to CMs. And say in the past, they were also called strategic resources, but this is old wine in new pipes. It's not a new concept. It circulated since the 19th century with a wood break, somewhat 1928, which arguably drove the move to fossil fuels. And with the rare earth supply discussion about 15 years ago, it heated up. And meanwhile, we speak about green technologies to enable a low carbon emission economy. So critical raw materials is an economic term, not a geological definition. And critical metals and critical elements are further synonyms. So the definition is not globally unique and will need to account for national or domestic industrial need, legislation and policy, and natural resource endowment. So if we look in the history, we see here how the metal demand has been multiplying over centuries from industrial revolution towards today's green revolution. So 17th century, we had mainly only carbon, calcium, iron. And if we move forward over the industrial revolution, the automobile introduction around 1900 until year 2000, you see how the demand in specific metals, critical metals, strategic metals was accelerating. So everybody is aware, mobile phones, we have the screen, we have the electronics, we have the battery, and you see here the list of the variable critical metals needed to run our mobile phones, which is a vital tool for many of us addicts. Mainly rare earths, but also lithium for the battery, indium for the touchscreen, and so on. Furthermore, equally important, like electric vehicles, it's new technologies. It's not just iron, copper, alumina. All over our modern cars, here a Tesla car in the picture, we see how the many different rare earth elements and critical metals are used. For electrical vehicles, it's mainly copper, lithium, cobalt, nickel, and for the rare earths, neodymium for the magnets, gadolinium, terbium, and dysprosium. Further, if we go for wind turbines, rare raw materials are needed to manufacture 1 3 megawatt wind turbine without including wiring to the grid. We need about 4.7 tons of copper, 335 tons of steel, 1,200 tons of concrete, 2 tons rare earth elements, 3 tons alumina, and zinc and moly. So this is substantial if we consider that meanwhile tens of thousands of wind turbines are added year by year all over the world. Photovoltaic cell technology. There's a demand for minerals, specifically silica, alumina, copper, silver, tin, lead. And so there's pressure on the resources which will increase due to increasing global population. And the existing and future photovoltaic cell technology will require a number of minerals for the frame, for the panel surface, for the encapsulant, for the black sheet, silicone, alumina, and so on. So here we see main materials, technologies, and sectors. And from left to right, the supply risk, the technologies from batteries, fuel cells, wind, traction motors, photovoltaic, robotics, drones, 3D printing, ICTs, and the main sectors are renewables, e-mobility, defense, and space. So we see this web where different rare metals or critical metals and rare earths are needed. And on the very top, very high supply risk is for the rare earth elements. High is still for magnesium, niobium, germanium, borates, and scandium. So here we have the classical matrix, supply risk versus economic importance. This is a critical metal scheme of the European Union from 2020. Just 2 weeks ago, the United Kingdom released its criticality matrix for 2024. And we see here sets periodic system of elements, and in the scheme I still show in orange the critical elements for 2021, and on the right side I show you in yellow background the 10 critical metals which have the highest priority now. Cobalt, gallium, germanium has been added, magnesium, niobium, rare earth elements, and tungsten, and added have been phosphorus, ruthenium, and rhodium to the top 10. And the list doubled from 18 to meanwhile 34. So compared to 2018 production levels, we see here the annual demand from energy technologies until 2050 on the left, percentage, on the right in millions tons. And at the top with the highest demand are graphite, lithium, cobalt, and indium. And for the million tonnage demand, it's alumina, graphite, nickel, and copper, and the base metals zinc and lead. So 3 of the most important critical elements are shown here: cobalt, lithium, and nickel. And the global demand and supply is shown. And in the right graph, you see especially from 2020 to 2035, the kilotons demand is accelerating equally. Most important for nickel, followed by lithium carbonate, and a little bit less for cobalt. So here's a table which shows the critical materials, and for the target years at the very right, 2030 to 2050, we see the projected demand increase up to 1,000, 1,200 times, 1,000 times for alumina from bauxite, 1,200 times for copper, and a few other elements like cobalt, nickel, manganese, lithium are all 1,000 times increase. This is substantial, and we simply don't have so much discovered deposits, and it's a lot of work to do for exploration. So this is from US Geological, from EAA. The total copper produced over the course of whole human history has been 700 million tons. But we need an extra 1.4 billion tons new copper needed to reach net zero by 2050. So in the two cubes show the increase in demand for the next 25 years. Here we see a map of the production concentration of critical metals and top metal producing countries across the globe. And you see, Russia, China, North America as the main production countries. And I dropped out here. Kazakhstan for Central Asia, uranium with 37% share, chromium with 16%, and rhenium with 6%, and equally Uzbekistan 6% of rhenium. So for this, 2 countries, 3 commodities play an important role in the Central Asia region. Another diagram, another map from Geological Survey of Sweden. And we see here the global production of critical raw materials. And of course, China is dominant, followed by US, followed by Brazil, South Africa, DRC, and Russia and Australia. So, and if you look into Central Asia, we have Kazakhstan with phosphorus, barium, and a few others. So phosphorus, 9% of the world share, barium, 7%, significant proportions of germanium, gallium, scandium, vanadium. And in Central Asia, we have to mention Tajikistan with a share of 8% in the global antimony supply. So here we see top global producers, mine production, and again, the dominance of China with this long list of elements. Russia, palladium controlling, Brazil, niobium controlling, South Africa, platinum, DRC, cobalt, tantalum, Australia, lithium, and Vietnam, bismuth. So, but Kazakhstan and Central Asia, empty, terra incognita. Why? The region is underexplored for critical metals. It's a net exporter of bulk or concentrate. There has been very little selective refining. Critical metal recovery requires investment into high-tech solutions. And this was not taken into account over the last 20, 30 years. There's a little valorization of byproducts, and exceptions are only the big mining metallurgical combinates like Kazatomprom, Kaz Minerals, ERG, Kaz Zinc, and in Uzbekistan, Navoy and Al-Malik, where rare earths from Kazatomprom is recovered from the in-situ leaching, rhenium and osmium from the copper ores, like Cheskaskan, Kalmakyr, and scandium, vanadium, gallium, and germanium are mainly extracted by ERG and Kassink and others. So, circular economy should be mentioned. It needs raw material, needs stocking, but it leaks the system from the exploration over mining, processing, raw material use, and further to design production. We have losses. A share goes into waste. This needs to be recovered, but in addition, I showed you in the previous slides, we have a growing demand. Unfortunately, for instance, lithium recycling is only about 1%. Rare earth recycling from magnets, for instance, is less than 1%, because in many cases, alloys are used and it's very expensive to recover pure rare earth elements. So that's an important slide when we speak about critical metals. This metal wheel is depicting various losses and recoveries possible on the back of metallurgical systems. So metals and their minor metals are recovered through the shown carrier metals like iron, copper, alumina, base metals. And inevitably, the losses from the system appear due to its chemistry and technology infrastructure. And this shall show the connection. So if we speak, for instance, about copper ores, we have by diatochy, by mineral system styles and deposit types, usually connected rhenium and moly, gold and silver, tellurium, germanium, cadmium. If we look in base metal ores like lead and zinc, there we have tellurium, germanium, indium, silver, gallium, cadmium, which come as byproduct metals with the base metal ores. So usually the big mining companies go for the big money, which means zinc and lead. And in the smelter as a byproduct, we have then these critical metals. For instance, most of the world indium production comes from the Teck smelter in British Columbia. Indium is practically solely recovered as a byproduct. There are no indium deposits sensu stricto. So, Central Asia is a missing link in the analysis of critical materials for the global clean energy transition. And we compare here from left to right, Kazakhstan, Uzbekistan, Tajikistan, Kyrgyzstan, and the number of metals which are produced. So for Kazakhstan, these are 16 elements. For Uzbekistan, 11 critical metals or main elements. For Tajikistan, 5, and for Kyrgyzstan, 3, with high importance for the global clean energy transition. So, but it shows how important Kazakhstan is as a commodity basket. Germanium, gallium, indium, tellurium, and graphite are present here in only one country each. So, a look at the literature and publications show that China publication sector is very active and understood the importance of critical metals research. 34 mentionings from 2009 to 2021 in database academic literature on deposits discoveries. If we look and US 16, South Africa 8, Russia 11. So if you look in Central Asia, critical metals practically don't play a role. The importance is not yet recognized. So now we jump into geology to set the stage for the geodynamic metallogenic framework. I mentioned already Central Asia is a commodity basket. It has a huge mineral potential, a huge endowment, but the exploration maturity is mixed. There are regions where it's high, there are regions which are largely underexplored. So, and I will introduce a little bit into the jigsaw puzzle of old continents, arcs, basins, and sutures. Here we see the geological map from the Atlas of Geological Maps of Central Asia and adjacent areas. And Central Asia is sandwiched between the old cratons of Siberia, Eastern Europe, Tarab, and North China craton. And we have in Central Asia, sensu stricto, famous deposits like Aktogai, Kaunrat, Boshakol, Norkaskan, and in Mongolia, I showed at least Oyutolgoi. All these deposits, especially the gold deposits with their byproducts, silver, selenium, tellurium as critical metals, underlay a structural control through thrust, folds, faults. There is a lithology control, redox barriers, an inheritance by crust recycling. There's a fluid control for the orogenic gold deposits, mainly decompression fluids in highly metamorphic areas, and magmatism plays a big role, either post-collisional granites for the gold deposits, for the orogenic class, or subduction magmatism for porphyries. So there are two major types, accretionary orogeny. Here I show you the different deposit types from a compilation from Petrov et al. 2008. And we see the geotectonic cycles which control VMS deposits in rifting environments, in back arc basins. We have gold deposits related to gold quartz, to extensional structures. We have the porphyries, the orange squares related to accretionary orogeny related to the subduction zones. And the second type is within plate or intraplate magmatism in tectonic settings, where large uranium deposits, nickel, copper, PGE, magmatic sulfide deposits, and epithermal deposits are related, but also carbonatites and a few other mineral deposit types like kimberlite-related diamond deposits. So now a few words about the Altaid Central Asian orogenic belt. We see here the commodity basket in our mineral deposits GIS coverage. Robin Armstrong, my colleague from the Natural History Museum, pulled this together. There are about or more than 10,000 objects were combined for Mongolia, Kazakhstan, the Urals, Central Asia. And we have data gaps, data bias for China by reasons of confidentiality and accessibility. And we don't cover here Southern Siberia and Russian territory. So anyway, we see here, these are the known deposits, the discovered deposits, but the endowment is certainly much higher from prospectivity mapping and predictive approaches. So we did an approach of showing distribution of deposit types grouped in 6 classic old Soviet styles, mesothermal vein stockwork, granite-related stockworks, usually rare metal granites belong to this group, porphyries, sediment-hosted disseminated share zone-related. These are the orogenic gold deposits, for instance. We have the epithermal vein stockwork deposits, and we have the VMS deposits. So, but where to look for critical raw materials, for critical metals, for minor metals? In which of these mineral systems should we look for what elements? So here we see a scheme from UK Research and Innovate, and this schematic section shows the geodynamic environments in which critical raw material deposits form. And we see the oceanic crust, its subduction for the oceanic arc. We see subduction under the continent, forming a continental arc, post-collisional magmatism, controlling rare metal granites, and we have back arc rifting, which with a large group of elements. So here are the mineral deposit types, and for each of this geotectonic setting, we have specific groups of deposit types and critical metals. So mineral deposit search will enhance our exploration models and our ability to identify new deposits and new styles of mineralization. All this highlights a key role for advanced geoscience. Can we identify new deposit types if we understand the geotectonic setting? We need a thorough audit of known deposits for the range of critical metals. This demands better mineralogical knowledge to map mineral residence. We can then also identify possible co-recovery and waste strategies. A lot of the critical metals are in tailings, in waste piles of previous mining, of previous centuries even. So, and this requires a closer link between exploration, mining, mineral processing, and downstream market for users, from geometallurgy to product design. So we see here now from the Circum Central Asia GIS, the geological map that we developed as a digital geological map in about 1 million scale. And I show this here to express that orogens are divided into 3 end members. According to Wang, IGCP 662 from 2018, accretionary orogeny, collisional orogeny, and intracratonic settings. And this we have all 3 in Kazakhstan. In North Kazakhstan, with Kochetav massive in the center, we have a collisional orogen. The old Kazakhstania craton, Riphean slivers and older, and there is accretion of arcs. In central Kazakhstan, we have primitive oceanic island arcs which collide and form this accretionary orogen through amalgamation to Kazakhstania. And in the east, we have the extensional magmatism and Wissen plate orogen of the Kalbaner Rim and zone and Irtish zone, with links to mafic underplating, or some scientists claim it's the Tarim influence, which causes the orogenic processes. So, and of course, in the west, we have the Urals, which is a ribbon orogeny, but of the group also of accretionary orogen. So we designed with a PhD student from East Kazakhstan Technical University this scheme to show in a section for Kazakhstan example, continental arc collision to ocean island arc collision, and there's the settings for collisional orogeny, for rifting or intraplate orogeny, and accretionary orogeny. So, and in Kazakhstan, this explains us why do we have in certain zones more syncollisional granites, in Kochetav massive anatectic processes in a thick crust with deep roots. Then in the eastern Kazakhstan, post-collisional intraplate magmatism hosting the pegmatites of East Kalba, and in the accretionary zone of central Kazakhstan, subduction magmatism, with a different distribution of S-type granites, I-type mixed granites, A-type in East Kazakhstan, and again I-type in the accretionary zones of central Kazakhstan, mainly volcanic arc granites or TTGs, adakites. Various Wissen plate granites are dominant in East Kazakhstan, Kalba region, where we have LCT pegmatites in East Kalba. In the arcs amalgamating to the Kochetav massive in North Kazakhstan, we have more S-type granites. And in the accretionary zone of central Kazakhstan, we have mainly Kreisnors in the post-collisional granites, forming deposits like Karoba, Akchatau, and Kokten coal. So, if we look now in the temporal distribution, the metallogenic evolution of Kazakhstan and also Uzbekistan in space and time has 4 main epochs: early Paleozoic, mid-Paleozoic, late Paleozoic, and Mesozoic. And I show here typical metal associations and critical raw materials or critical metals contained in the ores. If we look for ophiolites related to oceanic crust rifting, this hosts chromites, PGs, and nickel copper in magmatic sulfides. If we look for subduction magmatism in the accretionary collage, we have copper, subduction-related porphyries, but also VMS in back arc basins. If we look for accretion and collision, we have gold, uranium, and tin, and other critical metals. The byproducts are vanadium for the ophiolites, For the subduction magmatism, rhenium, germanium, scandium, and osmium. For accretion collision, it's indium, rare earths, selenium, tellurides, for the uranium also. Within plate magmatism controls critical metals, tin, tungsten, but also rare earths, lithium, niobium, tantalum. And in the sedimentary platform cover of Kazakhstan and Uzbekistan, we have uranium, sedimentary copper deposits in the molasse, and in the regolite, bauxite, laterite, we have gallium, scandium, and rare earths. So, CIRCAMS produced this critical metals map for Central Asia, Kazakhstan in the north, Kyrgyzstan in the south, Tajikistan most south, and Uzbekistan in the southwest. So our ArcGIS database holds a mineral inventory comprising more than 2,200 deposits based on major and minor commodities, and it allows a mineral assessment of critical metal potential. Here's a legend with the labels and the symbols for chromium, cobalt, yttrium, niobium, vanadium, copper, tin, rare earths, scandium, nickel, antimony, PGEs, lithium, tantalum, tungsten, and alumina. This is according to our evaluation, the key critical metals for Kazakhstan and Central Asia. Using a modern mineral system approach, the questions are: what controls the critical metal distribution in space and time? When and why did the mineralization form? Where can we find these deposits? What is the endowment and what is the exploration maturity? And for this, we need to look in basement. How deep is it? Where are the basins which are fertile? For instance, with vast rhyolite offsets on the big plutones, which were maybe eroded and formed similar. So where are the belts undercover and where are the faults? So here we see the geological and mineral deposits map of Kazakhstan and Central Asia, which CIRCAMS produced and updated since 2003. So it sees now into 20 years of its existence, and we regularly update and upgrade this product. Here we see the faults distribution map of Central Asia, and here the gravity anomaly map and the magnetic anomaly map. These maps help to understand the geological controls together with the geology and the structural map to identify fertile regions. So if we look now in a paleo geographic and structural tectonic map of the terrain reconstruction produced by Alexeyev and published by Lindsley and others in 2007, we see here the Kazakh orocline with the oldest formations, the early Paleozoic hosting Bakirchik, the oldest porphyry deposits in whole Central Asia. Then we have the so-called Devonian arc hosting Norkaskan, Silurian Devonian, and in the innermost part we have the Balkhash-Ili zone, which is the Carboniferous Permian arc. And its Pangdang is to the west, the Chatkal-Korama arc, which extends into the eastern Urals, where it hosts the porphyry deposit of Benkala. And in Uzbekistan, it hosts the giant Kalmakur deposit. So, and we did terrain analysis to show accretionary wedges, future zones, microcontinents, volcanic arcs, sedimentary basins, and so on. And this allows us, together with a petrochemical analysis of the magmatism and alteration, to identify fertile zones with high prospectivity. Here, a similar, a little bit more simplified tectonic scheme, and I drop out here the key deposits for Kazakhstan. So in the Cambrian oceanic arc formed Boshakol deposit. Then in the Ordovician Silurian arc related, we have Vasilkovskoye on the arc which accreted onto the Kokshetov massif. Koksai, with 440 million years, is about here, part of the Stepniak North Tian Shan arc. And then we have the Silurian Devonian arc hosting Norkaskan, 430 million years. That's here at the boundary, stitching through the Devonian arc, actually. Then we have the Devonian arc to Carboniferous Permian, hosting in the Balkhash Elite segment Kaunrad to Octogai, 330 to 325 million years old. Don't get confused, besides the calc-alkaline Kaunrad deposits, there's also eastern and northern Kaunrad, which is alkaline, a rare metal granite, which was dated at 300 million years. So we have practically a change in the system from compressive calc-alkaline magmatism to extensional post-collisional alkaline magmatism in the Kaunrad region. So finally, we have late to post-orogenic magmatism, where we dated Cheskaskan around 300 million years, and the stitching gold deposits of the orogenic class like Kumtor, Bakirchek, and Mohontau, all around 300 million years old. So the peak of gold mineralization is at 300 million years, and we call this the jackpot event. So from some statistics, we learned that for Kazakhstan, it is #1 in the world for chromium ores, uranium, silver, #2, lead and manganese, #3, zinc, #4, and so on. For the critical metals, cobalt and titanium, #9 in the world, and alumina bauxite, #13. So, and examples of Kazakhstan potential for future metals, the ranking among the global top 10 includes the following elements: uranium, cobalt, nickel, tin, lead, zinc, silver, manganese, iron, alumina, titanium, chromium, and gold. Underexplored to date are lithium, rare earths, and indium. In Kazakhstan, Kaz Minerals with copper, rhenium, and osmium production, and Kaz Zinc from their base metal production, also producing 4 or 5 different critical metals like cadmium, selenium, tellurium, and others. 2 deposits of the future are Verne Kairakti, one of the world's largest tungsten deposits. The byproduct potential has not yet been studied. Syrenbet is one of the world's largest tin deposits. And I will a little bit later speak about this and as an example that indium, lithium, and rare earths are underestimated for Syrenbet. So here we see now the map of licensed objects and areas of ore deposits for Kazakhstan, and it's a busy place in central Kazakhstan. You see all the blue labels and the exploration tenement areas in North Kazakhstan, gold exploration largely. Here is mainly copper and base metal exploration. We have vast activity now in East Kalpa for lithium pegmatites, and since long the Urals area and Mugochar is activity area for chromium, massive sulfide deposits, porphyry deposits. That's the license map, which I borrowed from Mining's Eurasia 2022. And you see the vast exploding exploration activity across Kazakhstan. Only very few virgin-free areas are shown. Everything else is largely covered either with exploration activity from the state or with activities from investors. So here, a map of critical materials for Kazakhstan, Kyrgyzstan, Tajikistan, Uzbekistan, the proven resource for Central Asia. And at the very end, I show Central Asia's share of global reserves in percent. So, and we see manganese, almost 39%, chromium, 30% of the world production. Or of the proven reserves, 30% of the proven reserves. This is substantial, and lead and zinc are number 3 and 4 with 20 and 13% of the proven reserves. So here we see the production and the rank in the global scale for Central Asia. Chromium number 2 in the world, cadmium number 2, selenium and zinc number 6. If you look for Kazakhstan, chromium number 2, for Central Asia, for the world, cadmium number 5, and so on. So I will not go in further detail. Kyrgyzstan, Tajikistan, Uzbekistan are shown here. And important is for tellurium in Uzbekistan, number 8, mainly from the gold and copper production of both countries. So now a few commodity maps from our GIS database. Here in green, copper as major commodity. And you see copper distribution in the Kazakh orocline, but also in the copper VMS of the Rudny Altai and in the VMS and porphyries of the Urals. And of course, also in Central Asia, in the Tian Shan region. So that's a different feature of the copper distribution map with individual deposits listed. And we see this cluster in central Kazakhstan, Boshakol, Kaunrat and Aktogay, Benkala in the eastern Urals. And most important copper and gold deposit is Kalmakyr in the Chatkalkorama of Uzbekistan. So if we speak about all these deposits and databases, we need to take into account that the future metal potential is at depths undercover. And we know since the Kauldi research deep drilling, which went up to 3,000 meter depths in the Chatkalkorama, and from most recent drill activities from SRK and the Uzbekistan government, that the Chatkalkorama has a huge mineral potential open at depths to 1,000, 1,500, 2,000 meter depths. And we see here from the Kauldi deep drill hole that copper and critical metals included in sulfur salts, bismuth minerals, and sulfides are up to 3,000 meter. So this is largely underexplored still and gives hope for the future. So here, this is a gold distribution map for Central Asia, the classical gold province of the Tian Shan, from Kizilkum to Kumtor. Then we have the gold VMS, like Ridder-Sokolnoye, Bakırçık in East Kazakhstan, Vasilkovskoye, the Charsky zone, and gold deposits of the Urals. But again, the largest gold deposit in Central Asia is the copper porphyry of Kalmakyr. Kalmakyr has meanwhile, with 5,700 tons, contained gold, more gold than Moruntau, with about 5,000 tons. So these are the famous gold deposits, Moruntau, Kumtor, Jilau, as some examples from Uzbekistan, Kyrgyzstan, and Tajikistan. And I show this because of the byproduct critical metal potential: selenium, tellurium, silver, bismuth, tungsten, and antimony. So this is a lead, zinc, and silver map. And if we look for critical metals, then we can look in most of the base metal deposits where we can expect selenium, tellurium, and many other critical metals contained in the ores. That's for iron and manganese, and very posh and fashionable right now, rare earths. And we see here the major rare earth zones in the iron-sorptive clays, in the laborites, weathering crust or regolites in East Kazakhstan, in North Kazakhstan. We also have some carbonatites. We have rare earth mineralization in the Kalba region, in central Kazakhstan, Karaoba, Akchatau. We have Akbulak as an important deposit of the future, Kundibai, Vernier Espe, and a new discovery recently published from the Committee of Geology and the Ministry for Geology or Ministry for Industry in Kazakhstan, around here in northeastern Kazakhstan. And of course, in Uzbekistan and in the Tian Shan, probably the most important deposit is Aktyus in Kyrgyzstan. So here we look at the distribution map. Green are rare earth deposits, where rare earths are major commodities, and they are spread over a range of deposits in carbonatites, pure alkaline and alkaline related rocks, pegmatites, granitoid related, epithermal, intrusive mesothermal, exhalative. Most production to date comes from sedimentary deposits, uranium deposits, Kazatomprom mainly, in the uranium, phosphate, vanadium, moly type, from in situ leaching and yellow cake. Rare earths are byproduct. In Uzbekistan, we know that in the coal is rare earth potential, and in the weathering crust all over Kazakhstan, we have important potential for rare earths. And of course, plazas and paleoplazas, where we have monazite and xenotime in northern Kazakhstan and in the Irtysh region. Okay, when we speak about rare earths, we need clearly light rare earths and heavy rare earths comprise this group, but also yttrium and scandium are part of it. So, and in reports, we find rare earths and yttrium. Scandium is sometimes included, or terre rarem, and as oxide. We must not confuse it with rare metals. In the recent newspaper reports is the language about rare earth metals, but this is referring also to rhenium, osmium, niobium, tantalum, and lithium. Those are not rare earths. If we mean rare earths, these are the lanthanides, from lanthanum to yttrium and a little bit scandium. All the others here in blue are not rare earths. These are rare metals. We should not use the term rare earth metals. So, lithium. I come to the end, last 2 minutes. So, this is a BGS lithium future map, but we see here for Russia, Kazakhstan, Mongolia, Afghanistan, no entries. So, this is now the lithium deposits map of Central Asia that my team produced. And we see green lithium as major commodity, and there are 5 deposits, all in the Kalpa region. Our database has more than 100 prospective lithium-bearing objects of interest. And where you see published map, the world map of lithium has for former Soviet Union, Mongolia, Afghanistan, less than 10 objects. So on the geological map here, some of the most important sites. Of course, the Kalba zone, this is the jackpot with many exploration licenses, Bakenoye and Akhmetka Akhmerovskoye, Nova Akhmerovskoye, and Jubilenoye. But don't underestimate Syrenbet Kreisen deposit has the largest tonnage of lithium in lithium mica. And we have Karagaili Actas, also a Kreisen deposit. Very important is in Uzbekistan, the Shavasai deposit, which is a volcanic sedimentary mineral system. And a lot of noise is about brines and salars, riverbed salars and oil brines, evaporites in western Kazakhstan. So, niobium tantalum deposits, tin tungsten deposits, I mentioned already, Verne Karakti and Syrenbet. And here is the map of tin distribution, tin deposits. And we see all over Kazakhstan and Central Asia. And there we have a lot of critical metals as byproduct, lithium, niobium, tantalum, also rhenium. So cobalt and nickel related to ophiolites and to mafic, magmatic mafic sulfides. Alumina and scandium related to regolite weathering crust. Chromium and PGE mainly to ophiolites and Alaskan-style intrusions. Here's a map of the ophiolites, and in red I circled for Kazakhstan about 12 different ophiolite zones which have potential to PGE, nickel and copper mineralization. Okay, and antimony vanadium is shown here. Okay, I think time is coming to an end. I should mention that for the antimony belt, there is a huge potential also for gold. And gold is, from some experts, also treated as a critical metal because exploration needs gold discoveries to drive their exploration for critical metals. So, and that's why antimony and mercury deposits in the center, in the Tian Shan, especially in Kyrgyzstan along the Nikolaev line, which is a North Tian Shan suture, and the Turkestan suture, which is a South Tian Shan suture. There is a major distributional control for critical metals. Okay, I think I will finish here. And okay, where we are. What I wanted to mention is this. If we look into Kalmakyr, this is now became with mineral resource calculation JORC from SRK, one of the world's largest porphyry copper deposits. It has a first place in the world from the gold resource with 5,300 to 5,700 tons contained gold. It has a sixth place in the world with 45 million tons of copper resources. And it's a third place in the world with a total resource of 19.5 billion tons. So this is for copper and gold, but look at the critical metals: tellurium, selenium, tungsten, zinc, indium, molybdenum, all byproducts of Kalmakyr super pit, which has enough reserves for 100 years mining activity. And with this, I would like to finish. Thank you very much for the attention.
Reimar, thank you so much for that. That was great. I'm sure I don't talk just for me when I say it's not a topic that we bumped into on a regular basis. So thank you so much for that. There's already several compliments for you in the chat. So much appreciated. Thank you. So let me share my screen now. Here. So now is the moment. I'm trying to just, do you mind to drop your presentation if it's over so I can share mine?
Yep. Yes.
Thank you.
Okay.
Yeah, good to go. Let me share mine. There we go. Can you see it?
I see question and answer session slide. Yes.
Yes, perfect. That's it. That's the one. So now is the moment that you might ask questions to Reimar. As I said before, there is a Q&A button on the either on the top or the bottom of your screen, depending on your setup. So you can tap your questions, and we are starting to answer them during the next 10 minutes. And just a quick reminder that the presentation will be available later. It's being recorded, and it's going to be available on our YouTube channel and the SEG website. So be attentive about that, and it's going to be available. So the first question for you we have here, the first one is, thank you for your presentation. Are the CRMs the main product of these mines? Any byproducts like PGEs in porphyry deposits?
Yes. Especially the porphyry deposits which have juvenile input from subcrustal lithospheric mantle, refertilized as CLM. These deposits have PGE, and whereas calc-alkaline, purely calc-alkaline TTG related porphyries are less complex. So, and for instance, Kalmakyr has about 20 different byproduct or critical metals which are produced. Pashava and co-authors published the enormous tonnage of PGEs for Kalmakyr. And in addition, osmium is the most expensive metal, and the plant, the Almalik plant, is producing this isotope, which is especially for radiochemistry important. For radiomedicine, yeah, nuclear medicine. Okay.
Excellent, thank you. We do have some other questions in here. Great talk, thanks. Is it required to upgrade typical or deposit models according to its geographic location?
there are some ore deposit models which are relevant probably only for Kazakhstan. We have this North Kazakhstan uranium moly vanadium phosphate type, which is unique. Of course, we have Cheskaskan type, which is a little bit African copper belt, a little bit Kupferschiefer, but it has specifics. So that means not there are specific deposit types just for Kazakhstan, Central Asia, which lack equivalents elsewhere in the world. We are still looking for Olympic Dam in Central Asia. There's some speculation about the Actius cluster, where we have very similar magic questions and disputes. But overall, I think the mineral system approach, the more general it is, the more helpful it is. And if you go in too much specifics, then each country has its own deposit types.
Yeah, excellent. Thank you. And the next one, I think we have a couple of minutes. Is it economic to mine a porphyry at 3,000 meter deep in this location?
Yeah, if we want to survive, this is where the journey goes. And there are a few porphyry deposits which are mined, I think, to 1,500 meter nowadays. And if we want our 300 times, 500 times, or 1,000 times acceleration of supply to meet the demand, we have to go deeper. This is not necessarily underground mining how we know it, but there may be to make shafts or to make drill holes and to send an army of 1 trillion of bacteria down and to create a good environment to keep them hungry and then to recover them through a recovery drill hole, something like this. I think it's probably much easier than asteroid mining, and I would not touch the ocean floor.
Thank you. Maybe we have time for one last question, which is, there we go. Dear Reimar, thank you for your interesting and detailed talk. In the following years, would you expect changes in the distribution between lithium deposits, like pegmatites versus brine-related, which is likely to be of higher importance in the future?
That's a very good question. So we have the lithium triangle in Bolivia, Argentina, Chile, which from the carbon footprint is the lowest, most ecological, but we have an ESG problem with the water and with the local population. So if ESG is getting managed, if it's sustainable, then this is a major competitor. But we have large, vast, underexplored or not explored pegmatite fields all over the old shields, old cratons. And there I see a major trend in growth of supply. I don't think that other regions will quickly join these two big monsters, the pegmatites and the salars. Kreisen or lithium hard rock from granites has a far too high footprint with a carbon impact, carbon footprint with 22 to 24 tons of carbon per ton of lithium carbonate equivalent. So 20 times larger than for salar. Yeah.
That
Okay.
was excellent. Thank you so much, Reimar. I guess our time is up, but thank you. Thank you so much for being here. Thanks for your amazing talk. Now
Thanks, Beatrice.
Thank you.
Thanks, everybody, for coming.
So now we are moving forward to our next presentation. Who is going to be presenting the next one is Sarah Thayer from the Université du Québec à Chicoutimi. And that's all the French that I have for you. And as Sarah is an SEG Thayer Lindsley visiting lecturer, and I might presenting Sarah to you and then inviting her to speak with us. So here. All right. So her talk's title is Magnetite and Apatite Chemistry as Petrogenetic Indicators of Magmatic Systems and Applications to Mineral Exploration. So Sarah Thayer is an associate professor at Université do Québec à Chicoutimi in Canada, where she holds a Tier 2 Canada Research Chair in Geochemistry applied to ore deposits. And she's also a director of the Lab Mater, a geochemical laboratory world-renowned for analysis of ore deposit materials. And she specializes in using trace elements in the ore minerals, sulfides, iron oxides, chromite, apatite, to unravel ore-forming processes and to develop indicator minerals for exploration. And she has a PhD degree in geology from Cardiff University, UK, and an MSci and BA degrees in geological sciences in natural sciences from the University of Cambridge, UK. After a postdoc at UQAC on magmatic nickel copper sulfide deposits, she was an assistant professor at the University of Ottawa before returning to UQAC as professor in 2018. And Sarah was awarded the William Harvey Gross Award, which is a Young Scientist Award from the Mineral Deposit Division of the Geological Association of Canada in 2016, and the Society for Geology Applied to Mineral Deposits, SGA, as a Young Scientist Award in 2017. So, Sarah, I now invite you to join us. You might turn on your camera, come on screen.
Thanks, Beatrice. I'm just ready to share. Yep, here we go.
Okay, thank you. Thanks for being here.
Let me just get rid of these floating controls. That over the way. Hi, everyone. When I get this going, I have a bit of a cold, so I'll probably be coughing, sipping water. So I hope my voice lasts through it. We'll get through it, I'm sure. Let me just add the pointer. Yeah, it's a pleasure to give you actually highlights of two of my talks that I offered on this tour, and that's the mineral chemistry, trace elements of magnetite and apatite as petrogenetic indicators of magmatic systems and applications to mineral exploration. And I want to start right away with the applications. In fact, mineral exploration in glaciated terrains, such as here in Canada, where we have a thick cover of glacial till formed during our last glaciation, we have a history of using indicator minerals to help with mineral exploration. Now, indicator minerals, for those who are less familiar with these, are essentially heavy and resistant minerals recovered from stream or glacial sediments, and they essentially indicate either a rock type or the mineralization. So think of gold grains will obviously be a good indicator for gold mineralization somewhere further upstream of the glacier. So here is just a schematic to show you as the glacier eroded the surface geology, grinding up the rock into minerals and fragments. Essentially, those indicator minerals from the mineralization would be dispersed downstream, and knowing the direction of glacial transport, and by sampling systematically the glacial till or sediment, counting the number of these indicator minerals, you'd be able to vector back towards the mineralization that's buried under this sedimentary till by the increase of count of these indicator minerals. This was very successful in finding diamond-bearing kimberlites in Canada way back when, where they used garnet, essentially of a specific chemistry of garnet, to identify a dispersion train for buried kimberlites. More recently, it's also being developed for copper porphyries. So just the presence of the minerals is already a good indicator. More recently, with the developments and more readily accessibility of being able to determine trace elements in minerals, such as laser ablation ICP-MS, there's a lot of growing interest actually now lasering, getting the trace elements of these indicator minerals. So say you have some chalcopyrite in your sediments, so you've got some copper mineralization nearby. If you laser that chalcopyrite, the different chemistry of it is specific to the type of deposit. So is it from a copper porphyry? Is it from a magmatic nickel copper? So that is where the interest in lasering these minerals really comes from. And how I got into it back in 2011, was with Georges Baudouin from University Laval, my collaborator. He was really one of the first to show that magnetite, if you got the trace elements of magnetite from a whole range of different ore deposits here, magnetite's very common. See the list of different magmatic and hydrothermal ore deposits here. This was originally done by microprobe, you pushing it to the limit, 12 minutes counting time to get those trace elements. But he was really one of the first with his team to show that the chemistry is distinct for each different ore forming environment. So here's the porphyry field, Karuna type, IOCG, banded iron, skarn, and these are the magmatic deposits using this diagram here. Magnetite had been used before that using probe for sedimentary provenance studies, but this was really one of the first pioneering studies to try and use it for mineral exploration. Then when I did my first project on magnetite with him and Sarah Jane Barnes, we started to use the laser ablation to get more trace elements. And this is what I will show you, one of our key diagrams. You're able to, your environment from where your magnetite forms, be it magmatic or hydrothermal, is distinct. So what I'm going to try and give you a summary of over this talk is how we figured out which processes control the trace element variation. So this is more on the petch genetic side. So our approach was very much petch genetic, to have an understanding of what is controlling those trace elements. So for a long time, igneous petrologists have used vanadium, chrome in magnetite to track fractional crystallization. This is an example from the Bushveld lead intrusion. You see the vanadium changes up sequence through fractional crystallization. Some of these reversals can mean the injection of more primitive melt or the stratification in the melt. One of my earliest works was to work on magnetite from magmatic nickel copper sulfide deposits. So this is magnetite crystallizing from a sulfide melt. And now we're able to add a whole load of additional trace elements here that you need to get from the laser. We're able to now get sub ppm detection limits. And here's just to show you that the patterns, again, the magnetite from the two different ore types are very distinctive, and that was driven through sulfide fractionation. In the hydrothermal world, Patrick Nadol and his co-authors essentially showed as well that magnetite chemistry variation is reflecting the change in temperature of hydrothermal fluids in particular. This is essentially the same diagram of Dupuy and Baudouin that distinguished porphyry from banded iron formation. But he was able to show through the trace element chemistry of hydrothermal magnetite from a variety of different deposits here, where the temperature of formation was known through fluid inclusions, through oxygen isotopes, that it really is the temperature control here on the trace element. Now, I'll also talk in the second part about apatite. It's a new mineral that really fascinates me. Why? For me, because they co-occur. Apatite crystallizes with oxides in magmatic and mafic intrusions. Here is actually some mineralization. Nelsonite, we call it, oxide and apatite. But it is present in lots of other different types of rock types and mineralization. And here, this work on the apatite was done through my PhD student, Mary Kiefer. You'll see a lot of her slides during this presentation. So here in green are the trace elements that substitute for the fluorine-chlorine site in the apatite structure. The blue substitutes for calcium, the brown for phosphorus. So about 40 trace elements can be present in apatite through substitution. Not only do you have the trace elements, you can analyze the radiogenic isotopes like strontium, neodymium. I'll show you some examples of that later. Geochronology, you can also get from apatite. The UPV system is well known. I'll present to you the more or less brand new lutetium hafnium geochronometer, which is really opening doors for studying mafic rocks in particular. And of course, you can even get stable isotopes, oxygen and sulfur. In addition, apatite, its textures and zoning is visible under cathode luminescence. Here's a rather boring pattern, some very weak magmatic zoning maybe of apatite in green here from igneous and mafic intrusion. However, if you get any hydrothermal alteration or metasomatism, you can see that clearly just through the CL textures. So what I'm going to show you in the second half is, again, that the composition of apatite really reflects the magma composition and how we could maybe use that to determine provenance. And in fact, one of the early papers to laser apatite from a wide variety of ore deposits here, you can see porphyries, skarns, etc., by Mao, he used essentially multivariate statistics to show that apatite from hydrothermal ore deposits have a very different chemistry to those from the felsic host rocks, and very different again to those from carbonatites and alkalines. And then within the hydrothermal family, you can see the chemistry again is distinct. So just to give you some background on how we can get trace elements in these minerals, or any mineral really, in situ by laser ablation ICP-MS. So the laser ablation system is our sampling tool. You can either drill spots down into the surface of your thin section of polished block, or you can traverse raster lines across, so it is a bit destructive. Essentially, the ablated material is transported as an aerosol by the gas carrier into the ICP-MS, that's the mass spectrometer, and there it detects and measures the isotopic masses. So this is it gives you great spatial resolution actually when you do this. These are the counts per seconds of each of the isotopic masses in the mass spectrometer. So we analyze 30 seconds the gas blank, we turn on the laser, we drill across or drill down in our mineral. You can see there's the response for iron. We're in a magnetite here. You see all these other trace major, minor elements down to trace, ultra trace elements in your mineral. And as we like to do across grains, so either from the rim to the core, etc., you can see if there's any zoning as you go across. This is the time resolved vector. Also, if you hit inclusions, you'll get a sudden peak, you know, to avoid that, so not to contaminate your signal. And here's a typical igneous magnetite with X solutions of ilmenite. So that titanium was in solid solution in the igneous magnetite at high temperature. At lower temperature, it dissolves out as these X solutions. So with the laser, we typically use, say, around 50, 80 micron beam. We analyze a large volume surface of the magnetite. It mixes back in those X solutions to give us a better approximation of its original igneous composition. Compare that to the microprobe. You're using a 1 to 5 micron beam. You have to decide, do I analyze the magnetite without the X solution or just the X solution? Of course, we then have to convert our counts per second to calibration. Something else that is very popular with laser ablation is mapping, chemical mapping. Here is an example of magnetite, silica-rich magnetite that's beautifully zoned from El Laco in Chile that I worked on. Here is a microprobe map using a 3 micron beam, so very, very high resolution of zoning, you can see. On the right here was our typical laser system back in that day. It took about 3 hours to map this little grain. You can see there's niobium zoning with the silica in that case, something we weren't really expecting. We now have in our laboratory, I'm director, so I'm going to promote this for the next 2 slides. In scrutiny here, La Matière, we have a new one-of-a-kind instrument that has, with the laser, a time of flight, really, really fast new generation mass spectrometer that gives us really, really fast mapping and high resolution. So essentially, you can see here, this is now a couple of millimeters across. This is the same El Laco sample. You see the same zoning of niobium here, but also uranium. I never thought to look for uranium in these samples, but with the time of flight, essentially it gives you every single isotope in the periodic table. You don't need to select it beforehand. So you're able to see if there are additional elements that are of interest with this instrument. And I should say that a map like this took 45 minutes. That would have taken maybe a whole day to do with the old instrument. So now we can go really fast. We can do much bigger areas. This was our lab manager who took time off to do a PhD to get the instrument up and running. Essentially, we're now able to do here a 5 by 2 millimeter size map in 45 minutes. So now we've got the problem of having multiple phases rather than just saying a map of magnetite, fine. Here you've got 4 or 5 different minerals: apatite, magnetite, ilmenite, carbonate, pyrite. So for him, he was able to develop a better calibration tool in iLight to fully quantify every single pixel, even if there was a different ablation yield, we call it. So that's kind of the new developments we've been been doing in our lab. And then the most recent methods that have been developed with the University of Adelaide in particular is using the triple quad for geochronology of apatite. It was known to be useful for UPB dating because essentially in a triple quad you have two quadrupoles with a third one in the middle is your reaction cell. So you put in a specific gas that will react with one of the elements to help remove interferences that are problematic during analysis. So it would remove mercury from the UPB, and in the case of lutetium hafnium, it would help remove the interference of ytterbium. I will show you some results of that later, and it's really a game changer because lutetium hafnium, the closure temperature is much, much higher than the UPB system. So I'll be showing you, they have shown that it's giving you more of an igneous age, similar to the zircon. And we have this instrument, and we're going to be setting it up for next year. So let's get back to kind of the main theme of this talk, which is to show you which processes control the trace element variation in minerals. So let's go back to the basics. What we all learn at the undergrad level, trace element substitution into any mineral relies on ionic radius and charge. If you have a similar ionic radius and similar charge as your main stoichiometric site. So here is an example for magnetite, the iron 2 site, the iron 3 site. On the left, this is the partition coefficient, which is the concentration of an element in the mineral divided by that of the melt. So essentially, if you're greater than 1, your element fits very well into your structure. It has a high partition coefficient. It's compatible. So you can see nickel, zinc, cobalt are very compatible into iron and magnetite. And in the iron 3 site, you can see chrome and vanadium are extremely compatible into magnetite in the iron 3 site. The minute you are either too large or charge too different, your partition coefficient decreases and you become incompatible. So then as the partition coefficient controls essentially where the element fits, when you laser your mineral and you get a composition, a concentration, it essentially reflects how much concentration of that element was present in the melt or fluid. So for an example, if we laser aluminium in magnetite from an igneous system, we get about 1 weight%. As we have a partition coefficient of 0.1, you have around an order of magnitude, around say 8 to 10% aluminium. That kind of makes sense. In a hydrothermal magnetite, you always have less than 0.1% aluminium. That would mean that you probably had a lot less aluminium in your fluid. Again, that makes sense. Aluminium is highly immobile. You're not going to have much of it in your fluid. So essentially, the main message of my whole talk for today is that the trace element composition of your mineral essentially reflects the composition of the trace element in your melt. Of course, partition coefficients can change, especially for redox sensitive. So here, vanadium 3+ fits very well. But if you oxidize your melt or fluid, have more vanadium 5+, that now will be very incompatible into your magnetite. So you will have less vanadium in that case. So what we did when we were first faced with, we have now 30 trace elements in magnetite. How do we look at it all at one go and try and make some sense of it? So we developed this multi-element diagram where to essentially show that the pattern reflects this composition of the melt or fluid. So we did that by ordering the trace elements in order of increasing compatibility. So the elements most compatible into magnetite on the right, that's your chrome, nickel, vanadium, those the least incompatible on the left. We then normalized it to bulk continental crust. Why? Essentially, that is an andesite in composition and an intermediate composition. So when magnetite crystallizes from a melt, a silicate melt, basalt, you have to wait until it's essentially an intermediate andesitic composition before magnetite starts to crystallize. And so what that gives us is more or less a slope increasing to have the elements most enriched are those elements that fit well into magnetite on the right-hand side. Those that are depleted because they are incompatible. They don't fit into magnetite, even though it's there in the melt. So having a diagram like this to see all of it in one go helps us identify key elements and ratios to build new discrimination diagrams. So before I show you how we did that, I just want to give a bit of background, remind you guys about fractional crystallization in mafic magma chambers. So mafic layered intrusions. Zonation we see from the lower zone being ultramafic, the middle zone mafic, the upper zone intermediate and felsic, is the result of fractional crystallization, because those olivines, pyroxenes will take the magnesium, the nickel, a bit of chromite will take the chrome. So those elements will decrease, those are our compatible elements, will decrease from bottom to top of the magma chamber. All the trace elements, the incompatible trace elements that don't fit in the plagioclase or the pyroxene or olivine, essentially remain in the residual liquid and get enriched. So that'll be our iron, titanium, phosphorus, the rare earths, the zirconium, etc. So those elements will increase up sequence. Now we use in igneous petrology the anorthite content, that's the ratio of calcium to sodium in plagioclase. We use the magnesium number, magnesium over iron of olivine and pyroxene, that all decrease with fractional crystallization up sequence. So essentially, our nickel chrome decreases. I mentioned the iron, titanium, vanadium, phosphorus. So where to find these kind of deposits, magmatic deposits in an intrusion? If you want to, when you form sulfides, you want it to be nickel rich. You want it to form early on before the olivine takes the nickel. So they'll find in the most primitive part of your intrusion, the nickel sulfide. Whereas the vanadium, which goes into your magnetite, you will find that in the upper part of the intrusion, the more evolved part where you've got iron to form your magnetite, which will take the vanadium. And then right at the end, the most fractionated part of the mafic intrusion, apatite starts to crystallize with those oxides. So what we did was to laser magnetite from these different oxide layers at the top of various layered intrusions like the Bushveld. So the most, we call it primitive, so the early forming magnetite layer here will have will be the richest in those compatible elements such as chrome, nickel, vanadium here, and that's your deposits with vanadium. Magnetite layer at the very top, the most evolved part where you start to crystallize apatite, has the lowest chrome and nickel, and essentially, yes, you can see that they have the lowest nickel and chrome. But also the pink field here for the most evolved has slightly higher titanium, manganese, molybdenum, niobium, and tin. All the other elements on the left-hand side don't really change because they're highly incompatible into magnetite. So we see which elements change with fractional crystallization. And a thing to be really careful about here, or to take great note, is this nickel-chrome behavior. Essentially, in igneous systems, in all igneous systems, it's really important to note they behave together. So when nickel is high, chrome is high. When nickel is low, chrome is low. So that would give us a nickel-chrome ratio less than 1. Probably easier way to see it is just a simple biplot of nickel and magnetite versus chrome and magnetite here. They both decrease during fractional crystallization, basically a good correlation here. I put the line here of nickel chrome 1:1, so you can see they're always higher. Why is that? Because chrome has a partition coefficient of around 100. 100 times more chrome will go into the magnetite than stay in the silicate melt. The partition coefficient for nickel, 10 times more, will go in the magnetite than stay in the milk. So there's an order of magnitude difference in partition coefficient between chrome and nickel. That means if there's chrome in the melt or fluid, you will see it. It will fit very, very well into the magnetite. One last example here from layered intrusions. This is now the granite on the top of a layered intrusion, the most fractionated evolved melt. And you can see the pattern in yellow here. It has the lowest of all the compatible elements here, the low chrome, nickel, vanadium, cobalt, the lowest magnesium, as we'd expect. Low aluminium, scandium, titanium also. They tend to be titanium poor. And you'll see now an influence of this evolved melt. Granites are typically enriched in tin, moly, zinc, germanium. You're seeing that in the magnetite too from granite. Now, just a quick comparison of magnetite from hydrothermal systems. So here in pink is the magnetite from the most evolved part of an intrusion that has apatite with it. Compare it now to the examples I give here are high temperature deposits, so porphyry, IOCG, IOA. You can see they have a similar pattern that's very different to igneous magnetite. Essentially, they are much lower in titanium, in niobium tantalum, hafnium, zirconium, aluminium. Now, these elements, high field strength elements, are essentially immobile in fluids. Again, as I said, especially for titanium, which is compatible into magnetite, this low titanium is telling you just didn't have much titanium in your fluid to give it. Again, the most important thing here is the difference behavior for nickel chrome. Here, the nickel is high in these hydrothermal magnetite, but their chrome is not. It's orders of magnitude low. Again, chrome is the most compatible, an order of magnitude more than nickel. So that is telling us there's just no chrome in the hydrothermal fluids. And this we interpret to be that nickel is it's more mobile than chrome in these fluids. If we take a look at the low temperature hydrothermal magnetite here, this is from iron skarns, lead, zinc, silver veins, and iron formations. Overall, their pattern is much flatter, orders of magnitude lower than the blue field, that was the high temperature hydrothermal magnetite. Have the lowest overall abundance of trace elements, which Patrick Nadol showed at the beginning, probably is due to the lower temperature, as trace elements will be lower solubility at lower temperature. And these kind of deposits certainly are lacking the magmatic input too. So from all of those elements, we really proposed that nickel-chrome ratio here versus titanium was really key in distinguishing magmatic with the lower ratio from hydrothermal, because the behavior of nickel chrome and the abundance in magmaster fluids is clearly different. So now just finish the magnetite part with some kind of applications and examples for mineral exploration. Of course, the challenge here is that magnetite is common in nearly all rock types: hydrothermal, igneous, sedimentary, chemical, mineralized, unmineralized. So how can we discriminate magnetite in the mineralized rock from the unmineralized rock? So going back to this diagram of Dupuy and Baudouin at the start I showed you for deposit types. Those diagrams were just to get us excited about magnetite, show that it's different, and it's worth doing more work. Essentially, if you now take unmineralized rock types, so magnetite from mafic rocks, in gray and from granites, if you blindly plot them on a diagram here, you will mistake them for being from mineralization, which many people have done in the past. So instead, what you should do is to first filter out all the igneous ones on here before, because they're different from hydrothermal, before you start using a diagram that was made for essentially hydrothermal deposits. If we go back here, of course, the igneous magnetites that plot here from disseminated magnetite, they're not mineralization, although they plot here on the mineralized field. From our study, we're able to show that by using a ratio as simple as magnesium over vanadium versus vanadium and magnetite here, able to distinguish actually magnetite from massive layers that are mineralized in vanadium. This is data from the Bushveld. So this field here is developed from massive layers of oxides of magnetite that were rich in vanadium. However, if you analyze all the magnetites in the surrounding rocks that are disseminated, they plot always to lower magnesium over vanadium. So essentially there's a field for massive oxides versus disseminated oxides, which is great. Because you don't want to get excited about high vanadium in a rock type that's only disseminated. Why this magnesium is key? Because it's well known that magnesium lost through re-equilibration. So after the rock has solidified, for disseminated magnetite here, you can see it coexists with mafic minerals or olivine, pyroxene. Will exchange. There will be diffusion between the magnetite and the olivine or the pyroxene. The olivine will take the magnesium from magnetite and in exchange give it more iron. So hence this shift in magnesium that helps us discriminate massive, i.e. mineralized from unmineralized in igneous systems. And furthermore, one project I did here was to test whether magnetite could be actually used as a fertility indicator. So you take post-mafic intrusions. I took some that had known mineralization of nickel copper sulfides at depth. Those are the fertile samples compared to those mafic intrusions that did not have any nickel sulfide mineralization at depth. That's the barren field. Again, this is the nickel chrome diagram. You will see that this nickel with an order of magnitude less nickel for the same amount of chrome in the magnetite from these fertile host intrusions. So this is recording this nickel and also copper depletion from a fertile magma. Now, using whole rock, that's what many people use to evaluate the fertility of intrusions. Look at this nickel depletion and copper depletion in the whole rock. And essentially, as I said, as the magnetite composition reflects the magma, that is also recording this fertility indicator. So just to wrap up this magnetite section, hope I'm on time here. Essentially, magnetite has been used in a few cases to test cases around copper porphyry deposits using detrital magnetite. So this first study here by McCurdy et al. 2022 around Casino porphyry in Yukon. Essentially, he characterized magnetite from the bedrock. He took fresh igneous host rock, the granites, analyzed the composition, the altered igneous here, which is essentially from the hydrothermal system, has altered the igneous magnetite. Then the magnetite that crystallizes precipitates with the mineralization, and each one using linear discriminant analysis, he showed that they were distinct at this local scale. He then compared it on my diagram for nickel-chrome ratio, and I was very relieved to see that both igneous populations, even when altered, this is the green, even when altered, still plots in the igneous field because that nickel-chrome ratio has not been affected. And the hydrothermal magnetite plots well in the hydrothermal field. He then actually tested it to stream sediments around the porphyry deposit and was able to identify, based on his linear discriminant analysis and comparing it to my diagram, that all the igneous, fresh and altered plots here. This was probably a sample far enough away that you only had a few hits in the till that represent the mineralization. Whereas as you got closer to the mineralization, you suddenly had a much larger frequency of the mineralized signature from the hydrothermal magnetite in the sediment. And one last example by Piercey, again in British Columbia around Mount Polly, copper porphyry deposit here. Here they analyze magnetite from the ore deposit in pink, plotted in the hydrothermal field. They analyzed from the till. And the point here is, obviously, as we all know, that most of the magnetite in the till will be from the unmineralized host rocks, the background. Only a small proportion will be actually from the mineralization itself. And here is just to show that the proportion of mineralized versus non-mineralized in the till obviously increases towards the deposit and can be used to vector towards a known deposit in this case. So now, for the second part, I'll give a quick review on apatite chemistry. Again, show you it really reflects the magma composition and how we've tried to get people interested in using apatite to determine provenance for mineral exploration. So I'll start with how we've developed apatite as a petrogenetic indicator using mafic intrusions, and then finish up with how we can identify felsic from mafic, and then even distinguish the kind of felsic intrusion it was based on apatite chemistry. So this is all based on my PhD student's work, Mary Kiefer. You'll see her name everywhere. So we took essentially a well-known layered intrusion, mafic layered intrusion here in Canada, Sept-Îles, which had been studied in great detail before. This is the stratigraphic column. Essentially, this is the plagioclase composition, which was used by those who studied it beforehand to show how the evolution of the magma chamber from primitive to evolved, then a new reinjection of magma, several reinjections of magma, then it evolved to very evolved composition, and so forth. So essentially, in the blue boxes here, most of the intrusion contains very little apatite. In fact, it's intercumulus apatite in the most primitive part of the sequence. These are troptolites and gabbros, and this is what intercumulus apatite looks like, essentially crystallizing from the trapped liquid between our cumulus, olivine, and plagioclase. So we're expecting these to be enriched in incompatible elements and our volatile elements too. At the top of each of these cycles of fractional crystallization, there are apatite-bearing rocks. Essentially, these are now cumulus apatite from the most evolved part. An apatite gabbro here, you can see the apatite white, always with the oxides in black. And at the top of the second cycle, you actually have a deposit, iron titanium phosphorus deposit. This is the rock Nelsonite. Again, you can see these beautiful apatites with oxide. Then why Setzel was very interesting is at the very top, it has evolved to a granite. This is not from crustal melting. It really is the extreme crystallization, fractional crystallization to an A-type granite. And here there is plenty of apatite too. So Marie analyzed all of these different parts of the intrusion to show you how the chemistry varies between the felsic, the mafic, and then the difference between cumulus and intercumulus of the mafic. So first of all the magmatic apatite is fluorapatite. We can see here in the mafic part, the intercumulus crystallizing from that trapped liquid is definitely more enriched in the volatiles, chlorine and OH, as we expect. If we now look at her equivalent multi-element diagram here, sorry. In blue, what she's showing here are the two mafic populations. The blue pattern is the cumulus, so the most evolved part of the cycle, and the black hashed here is the intercumulus. So very similar pattern for rare earths. You can see there's a big hump here, that there is in fact an enrichment in thorium, uranium, as well as chlorine I showed you. So those are highly incompatible, enriched in the trapped liquid. We also see that vanadium is high. So it's enriched in incompatibles as well as compatible like vanadium. That's indicating that it's crystallized from the more primitive melt, although it's in the trapped part of that melt. So essentially, by looking at these patterns, she was able to propose key ratios and elements to discriminate cumulus apatite with that high chlorine, with low chlorine for cumulus, using these elements. So it's easy to discriminate intercumulus from cumulus. We then, as we had the whole sequence, here she has plotted rare earths, vanadium, and apatite versus the AN content of the plagioclase, which is our indicator of fractional crystallization from the more mafic to the most felsic. And as expected, the rare earths increase, along with thorium, uranium, all those incompatible elements. It's just a proof of a concept. The other thing that was very nice is that at Setzel, we actually know the liquid composition, how it evolves. This is calculated from mafic dikes, chilled margins, and the granites. So then she was able to show which elements decrease with fractional crystallization. You can see the vanadium rapidly decreasing from bottom to top of the intrusion, beautifully matching what the liquid composition was doing. So not only vanadium, but strontium decreases, the europium anomaly becomes more negative, as well as barium and magnesium decreases. So now comparing the red here to apatite from felsic rocks, you can see, as I mentioned, higher rare earths, larger negative europium anomaly, strontium has gone down. She was essentially then able to propose a simple ternary to distinguish mafic apatite from felsic apatite, with essentially strontium yttrium ratio decreasing as your rare earths increase. That's the fractional crystallization trend. Something also of interest to those who study ore deposits and mafic layered intrusions is crustal contamination. Now we know that affects the magma composition, we see an enrichment in the whole rock of incompatible elements such as lanthanum, thorium, lead, and uranium. Essentially here, just to remind you, this is a typical upper continental crust composition on a multi-element diagram. Here, the lower line is your oceanine and basalt, so a mantle-derived melt related to plume that is uncontaminated. Now, most of our continental flood basalt are contaminated somewhat by crustal material, as the melt has to cross the continental crust. You can see we know that these elements are enriched in the melt. Now, what happens when you look at the apatite? Indeed, this is now essentially your lanthanum-neodymium ratio. So that's the enrichment of your light rare earths. You can see in these green symbols here, those are from our contaminated lead intrusions, like the Bushveld. We even had samples from Sudbury impact melts. That is 100% crustal melt from a meteorite impact here in Canada. So that's giving you a high lanthanum enrichment due to crustal signature. Compared to the gray symbols here, these are apatite from uncontaminated or least contaminated magmas. So these are olivine and clinoproxene bearing intrusions like Thetsil, Skirgarth. So essentially, the lanthanum is definitely indicating crustal contamination. And also on the heavy rare earth side, this is a gadolinium terbium ratio here. You can see these high values. We believe they might even be able to indicate the depth of melting of our melt system, because the terbium is retained in garnet. So deep melting in the garnet field will give its signature to the melt, and the apatite is inheriting that signature too. Then, as I mentioned, we have the radiogenic isotope system. We can analyze readily now in apatite using in situ laser ablation multi-collector, ICP-MS. Very quick and easy to get the isotopic data now. So we did that in Marie's study and essentially showed that those contaminated intrusions, mafic intrusions, the apatite in the colored symbols here show intense crustal contamination and matches previously published data too. So now I've shown you that the diagram she originally proposed for based on a single intrusion. Now we know that different mafic intrusions can have different depths of melting. They can have different amounts of crustal contamination. When you combine all that data together, we had to modify this diagram because thorium lutetium now could be increased through crustal contamination. So that essentially changed the field for intercumulus in the middle here. And why we've really been doing this is because I work a lot on these kind of rocks, oxide apatite mineralization, and anorthosites and lead intrusions. And in some cases, there are no silicate minerals with them. They're just massive. So it's difficult to know how evolved was the melt, how contaminated it was. So these new tools really help for my research team to work on these enigmatic rock types in the field of igneous petrology. Often also there's no zircon in these rock types for geochronology, and getting zircon out of mafic rocks is also a bit tricky. I'll show you one application how we used this diagram to solve a debate actually in what is the mantle source to form anorthosite suites, Proterozoic anorthosite suites here in Quebec. The tectonic setting is argued over. Is it a mantle plume? Is it a deep mantle source? Is it contaminated? Is it a shallow mid-ocean ridge? Was there metasomatism? Everyone has put in a model. So by using apatite, I was able to get out of this intrusion here. I talked to like gabbro-lead intrusion, the host vanadium mineralization, the patterns here in red and orange. They seem very different on this pattern, on this multi-element diagram. In fact, they match very well the black line, which is apatite from mid-ocean ridge gabbros. So if we plot that ratios, it's much easier to see on this diagram. Indeed, the apatite from this Proterozoic mafic intrusion here in Quebec plotted very similar to mid-ocean ridge. So from that, we propose that it's depleted, shallow mid-ocean ridge-like source. So that's how these proxies, how these techniques can help us better understand the mantle source of certain mafic intrusions. Now, I promised that I'd show you some the new geochronology tool for dating mafic intrusions using apatite and lutetium hafnium. So this is a PhD student down in the University of Adelaide, where they do lutetium hafnium and uranium lead on layered intrusions that have apatite of known age, just to show how well lutetium hafnium matches the original zircon age. This is for Sudbury layered complex. Here's another example, Nebo Babel, mafic intrusion. Here's the zircon age, lutetium hafnium from 4 samples match that zircon age with an error. Most of the uranium lead do too. For 1 sample, as we know, it can be set. You lose that lead or radon with reheating, can be lost. And why I'm particularly excited, because I work on these oxide apatite mineralization in anorthosite massifs that form during an orogeny. So essentially, these rocks have stayed hot for a very long time at mid-crustal depths. So uranium lead is definitely going to be reset. And we see that with the example here from greater intrusion here in Quebec. The age of the anorthosite is here around 1008, 1060. The lutetium hafnium is giving with an error the same age, and the uranium lead has been reset by the last metamorphic event. So this lutetium hafnium of apatite really, for me, is a game changer. So just to wrap up, in a few minutes, just to show how some discrimination diagrams we think based on petrogenetic understanding, how we could use apatite as a provenance tool in glacial till stream sediments for mineral exploration. So why is it important to know whether you've got mafic source rock or felsic source rocks, whether it's I, S, or A? Because in each case, you have potential for a different kind of mineralization. See your iron, titanium, phosphorus. If you've got a cumulus apatite from mafic, if you identify intercumulus mafic, that means it's deeper down. Maybe it's the right kind of magma to form a nickel copper PGE deposit. Then your I types, of course, are related to your subduction zone porphyry systems, your S type to your lithium and your tin tungsten, and your A type to uranium niobium. So essentially, here's a suite of diagrams from data that she generated from felsic, mafic rocks and compiled from the literature. There's a lot of data of apatite from felsic rocks now, especially from porphyry system. So the first diagram is one that already existed in the literature, O'Sullivan et al., 2020. It's used a lot in sedimentary provenance. Here he proposed a field that combines a mismatch of all the felsic and mafic apatites that are different from this field to lower rare earths is metamorphic field, to higher is your alkaline field, and then your high strontium is your carbonatite field. So all of her data for mafic and felsic mostly plot in the right field, so that's great. That could be used to make sure you have a mafic and felsic and not something else. Then to distinguish mafic from felsic, we go back to the original diagram she proposed, rare earth, strontium, yttrium, europium anomaly, mafic field here, a felsic field. This is all her data from felsic. Mostly they plot correctly. Several, particularly the I type, plot to much higher strontium yttrium, which could be mistaken for mafic. So now she proposes that it's not just the strontium yttrium that's useful, but all the other incompatible elements. The lead, thorium, uranium, and arsenic can be used to distinguish better felsic from mafic. So now can we tell type I, type S, type A? So here is kind of an average for the 3 types: blue for I type, green for S type, red for A type. In mafic systems, there's no rare earth minerals to change the pattern of apatite, which is why it really reflects the magma composition. However, in granites, we are competing for the rare earths in particular with all these rare earth minerals. And in particular, S type and A type are known to have monazite, whereas I type doesn't as much. And we believe that's what's causing the different shape, the different slope of the light rare earth depletion in the cases where monazite is present. So in fact, the co-crystallization and this competition for the light rare earths is different for each of these granite types. Also, what we'll see in the next slide is that manganese is good to discriminate S-type, which is higher, and that is true. It's well known in S-type granites, they are richer, the melt is richer in manganese. We're seeing that in apatite. I-type is richer in vanadium. Again, those I-type granites are known to be more vanadium rich than the other granites. So again, for these elements, apatite's reflecting the melt composition of the granite. So if you combine the light rare earth slope with the vanadium and manganese, able to pull apart those three types. Of course, the boundaries aren't simple. It needs to be tested more, but it was really a proof of concept that the power of apatite in the trace element chemistry can distinguish these different types of granites. And my last slide here is, well, why do we care if it's a granite or a mafic or an ISA in the till? As I showed you before, most of the information we get from the till will be the host rocks. And I believe the host rocks are an important source of information. We're not just looking for the mineralized signature, but those host rocks will tell us. They can enlarge in the footprint by saying, do we have a prospective type of intrusion? If we're looking for nickel copper, we want a mafic signature, one that even has nickel depletion to show that we had a fertile mafic intrusion. If we're looking for copper porphyry in an area, we want to make sure we've got felsic host rocks. We want an I-type. And then more recently, people are using europium anomaly, strontium yttrium to show that which type of porphyry was fertile for this. So I believe you shouldn't just be looking for the signature of the mineralization. Those host rocks are also going to give us a lot more information in fill. And if you're a student and you're wondering what to do next, and you kind of like what I did, I'm looking for a lot of students to come to Quebec Scrutiny, so please drop me a line. And thanks to all my students and my co-authors, and that's it for me.
Sarah, thank you so much for that. That was amazing. I was looking into the chat and you have many questions already. You are starring here, very popular.
Will I stop my share so I can, hi. Sorry, I raced through that. I hope I didn't lose everybody. Too much to say.
No worries, and I'm going to share mine as well. There we go.
Thanks.
Yeah, you see my screen?
Yep, I see quite a few talks.
Yeah, no, yes, it's done. Yeah, so now it's time to formulate questions for Sarah. You might tap them, the Q&A set button by the top of your screen. And we already have some questions. Let me bring some to us in here. Here, let me just change my mode to share. Here. So the first one for you is, great talk, Sarah, really interesting work. Do you know if anyone is using this laser mapping for exploration? Even with the 45-minute faster mapping you show, there's still a lot of time for 1 grain. The trital indicator mineral studies often involve thousands of grains.
Yes. So essentially, to get data, if you would just do lines of 60 seconds, 30 seconds. That's what we normally do. I've just shown you that for us academics or students to understand the processes, that's where the mapping is useful. I wouldn't use maps certainly for exploration. You get, even if it's zoned, you can laser across it. That this 30-second, 1-minute signal per grain is essentially what we do most of the time. Just those maps, people love, they're beautiful. They can help you interpret complicated petrogenetic processes, but I wouldn't say that's particularly useful for exploration. So what I think most people would do or are doing is just do zap, 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 zap. They mount the grains in a puck, and you can get through hundreds and hundreds of grains in a day if you pre-program it. So that makes it a bit more applied.
Perfect, thank you. And the next one, there you go. The next one, has granite been found in heavy minerals from till? If present, could TE data on granite and in till be used as a pathfinder exploration guide for a metamorphosed zinc-rich deposit, such as VMS and SEDEX?
Yes, so that is, I haven't personally worked on that, but I know Paul Spry, a prof in the US, he worked a lot on garnite that is recovered in till, and it's exactly what he did, something very similar, using probe and laser trace elements for exactly that. So it's Paul Spry. So go on his Google Scholar profile, and you'll find his work.
Thank you. The next one, in apatite, what do we expect for the relation between strontium and europium?
So this is probably related to, so both strontium and europium go into apatite, but also, of course, into plagioclase. So in a mafic system where you don't have amphibole crystallizing either, the strontium decreases because you're crystallizing plagioclase. We see that with the apatite. Europium 2+ goes into plagioclase. So that's why, it's held back, that the other rare earths increase. So you're seeing this increasing negative europium anomaly. That's typical. So decrease in strontium and europium anomaly is typical in a mafic system. Now, I know you're probably more interested in the porphyry, and that's where they're using kind of the strontium yttrium ratio and europium because they're also sensitive to redox. So in a porphyry setting, Adam can correct me on this, essentially the yttrium is held back. So to form a porphyry, you want essentially a hydrous oxidized magma. That's what they're doing when looking for fertility. So essentially a hydrous means you're crystallizing a lot more amphibole, you're suppressing plagioclase crystallization, so you have a much less yttrium going in. So that will give you your high strontium over yttrium ratio, especially in these adachite melts. And europium anomaly won't be as great. It'll be very shallow europium anomaly, because A, your plagioclase doesn't crystallize much or not till very late. So you're not taking the europium 2+, and in oxidized conditions, europium 3+ fits better into your apatite. So yes, this strontium, yttrium, and europium anomaly is certainly also sensitive to the hydrous and oxidized nature of typical I-type melts. If that answers your question.
Excellent.
There's
Thank
a
you.
lot of literature on porphyries about that now.
Okay. And for the next one, we still have a couple of minutes. In apatite, what would be the behavior for uranium and thorium?
So as I mentioned, those are very, in mafic melts, they are very, very incompatible. So they are being enriched in the more evolved melt, and we see that. We see it also in that trap melt. So those intercumulus, because the trap melt where you often crystallize a bit of amphibole, zircon even, those are patches that are enriched in these incompatible elements. You see that. Now, if you crystallize monazite or other rare earth minerals, say from a granite, that might also take thorium, right? So you might see a decoupling of uranium thorium if you start crystallizing some of these other rare earth minerals from a granite, if that helps.
Yeah, thank you. Next one. Thank you for the helpful talk, Sarah. Speaking to the discriminant diagrams developed by Tupus, and these are hard names for me. I'm so sorry, I'm crushing it.
Yes.
Yeah, thank you. 2011, are these fields based on detrital magnetite samples only? Are these discriminant diagrams applicable to magmatic magnetite as well as developed purely based on hydrothermal magnetite chemistry?
So all of these discriminant diagrams, you have to start with known samples. So you saw the symbol list, they were samples of known locations, known hydrothermal, and they had some igneous, they had some oxide-rich vanadium and even titanium deposits there. So they were then later tested on till, that's for sure, but all these discrimination diagrams have to be tested on known samples to do it. Also, that was kind of a start to get everyone excited, almost what we're doing with apatite. Now, a lot of the researchers, including Georges Baudouin himself, have now gone to multi-variant statistic analysis, even now machine learning. And machine learning is impressive. It really is able to really pick apart very, very well these different signatures. People often think, it's a black box. It's not often what is causing this difference. That's where I think my approach is complementary to the machine learning. Probably the machine learning is more powerful at finding those differences. Certainly with the proficiency test, it comes out, the accuracy precision is incredible based from the model and then doing on the test set. But if you don't have a population in there, of course, it will misidentify it. So I think the two approaches are really needed. And of course, in both cases, you need known samples, you then test it on unknowns. But I think really what I'm doing, it's when we see, you know, the importance of a certain element in the discriminant model for something, understanding geologically why those elements are different in different ore forming environments or different processes, the two are needed together, really.
Excellent. We got some extra minutes, so just one more questions before the break, and that would be here. Just a sec. I lost my question. Just I found it here. Hello, Sarah. Really interesting talk. Lots of food for thought for exploration techniques for magmatic processes related to deposits. Do you have any insights into how similar methods could be used to explore non-magmatic processes related to deposits, like sedimentary copper through chalcopyrite snaps, as you alluded to earlier?
Yeah. So I mean, this is just the tip of the iceberg, really. There's a lot of interest developing for petronetic and provenance indicators. And for the more hydrothermal deposits, I can point you in the direction of my colleague, Georges Baudouin. With his research chair, he essentially is doing trace elements in all kinds of minerals, chalcopyrite. I helped on that project. Scheelite, gold, all these different minerals that cover all different kind of ore deposits. And certainly the work on chalcopyrite was really, really interesting, that with machine learning at the end of it, we migrated to machine learning, and that was really, really impressive how it could first discriminate magmatic chalcopyrite because of its high nickel, not unexpected there, from hydrothermal. And then within the hydrothermal realm of chalcopyrite, you could split up all the different kind of hydrothermal ore deposits based on the different patterns, the different concentration of trace elements in chalcopyrite. So there's a lot of research going on out there that cover certainly the hydrothermal deposits too. And so if you're interested, Georges Baudouin, it's on my talk. Go to his Google Scholar. You will see a lot of student research there. And there's a lot going on in China too. I can't name everyone, but
Thank you. So with that, I thank you once again for being here with us. I defended my thesis on trace element distribution. I wish I had watched this presentation earlier.
We should talk more.
Yeah, right. Definitely. So thank you so much. Thank you for being here. And we have some other questions for you. We don't have the time to answer. All right,
I will type them in.
But you can type them. Yeah.
Yeah.
If you're able to, that would be great. Thank you.
Thank you.
Thank you, Sarah.
Thanks all for listening.
Thank you. Next, we have Stephen Piercey with us. I welcome Stephen to join us. And Stephen Piercey is a completed bachelor's with honors and MSci from Memorial University of Newfoundland and a PhD from the University of British Columbia. From 2001 to 2008, he held the positions of assistant professor between 2001 and 2004, and associate professor between 2004 and 2008 in Mineral Exploration Research Center, MERC, and Department of Earth Sciences at Laurentian University. Between 2007 and 2009, he was the principal of SJP Geoconsulting, a St. John's-based consulting firm focused on the application of field and laboratory techniques to mineral exploration and development. And since December 2009, he has worked in the Department of Earth Sciences at Memorial University as an associate professor between 2009 and 2014, and as a professor between 2014 and 2021. And he's currently a university research professor since 2021 until now. And Stephen is a registered professional geologist in Newfoundland and Labrador, Ontario, and Saskatchewan. And now he's the SEG president, and I welcome him to join us. Hey, Stephen, you're welcome to present your screen. Thank you very much for being here. I'll stop sharing mine so you can share yours.
Okay, let me just get my presentation up. Okay. And can you folks see this now and hear me?
Yes, yes, we can.
Okay,
Looks great.
perfect. Okay, thank you. It seems like yesterday that I was given my presentation at the end of 2024. So 2020 or 2023. So 2024 has been quite a year and quite a good one. And it's been quite an enjoyable experience. And what I'm going to talk about today is just to look back on sort of some of the things that were the focus of 2024 for myself and my colleagues, namely the strategic plan. I'm going to mention the SEG 2024 meeting in Windhoek. A number of changes have happened within the organization. I'm going to give some thanks that are specific, but there will also be some more thanks coming at the end of the evening when Anne gives her presentation as well. But to start off, I'll talk firstly about the strategic plan. This has been the focus of a lot of the initiatives of 2024 by myself and others. It was a pretty prolonged process. It started in 2022, where there was a survey of about 20% of the membership, as well as a DEI survey asking key questions to gather information for the next phase of development of a strategic plan. This was followed in 2023 and 2024 with a variety of input from SEG staff, council, as well as SEG Foundation and Canada Foundation. And there were multiple meetings in late 2023 into about June 2024. And in June 2024, we created the high-level vision document that focused on core values, missions, and aspirations. And we've sent that out to a variety of stakeholders, including former presidents, council, long-term volunteers, and early career professionals and students committee, and got input between August and September 2024. We use this to revise it, and it's currently out with a number of our key sponsors and others for further commentary. But I'm going to highlight some of the key points here that will be coming out in the next little while. So the strategy really had a number of various pillars outlining what our key values are, the enduring principles that support SEG's mission. Our vision, this is sort of aspirational long-term goals that's articulated in the present tense to guide what we'll do in the next 10 to 20 years. A mission, what is it that we want to do? It defines who we are as an organization today and our shared objectives, and then a number of key aspirations that we want to focus on in the coming years and actualize on to improve the organization and our value for members. So to give you some of the key results, our values based on a lot of different discussions with others: excellence, integrity, discovery, knowledge, community, and inclusion. The vision statement: the society plays a fundamental role in advancing the knowledge of Earth processes and in applying scientific and technical knowledge to the responsible exploration and stewardship of Earth's resources to foster long-term sustainable development. And as a society, our main mission is a diverse global community of industry professionals and academics committed to the advancement of science, discovery, and responsible stewardship of Earth's resources, and support research, scientific dissemination, education, and professional development, innovation, integrity, mentorship, and partnerships for the benefit of human society. The main aspirations are really to produce the best science we can, highest quality, respected, and relevant publications in a variety of forms that represent the core knowledge for economic geology. We want to have conferences and meetings that share new knowledge and build collaborative relationships, provide the best professional development opportunities and content for our members that are valued at all career stages and reflect the diversity of career pathways that people take. A welcoming and global community that supports our goals of excellence in science and stewardship of Earth's resources, and ensure that SEG is structured, governed, and aligned to make sure that we make the best use of our financial, staff, and volunteer resources while prioritizing transparency, ensuring financial stability, and building institutional resilience. So this is sort of our guide. And where we have to go next is really about implementing this. So the plan for the coming year, and we'll talk more about that later on, as an implementation plan. How is it we execute this? So we're going to be reaching out to staff, leadership, and key volunteers to create an implementation plan. The fortunate thing is that during this process of consultation, there's been a lot of suggestions provided for various steps to execute. And so we're going to implement a lot of those points that have been made. And there's been a lot of input from staff who will really be the people that lead this execution daily. And it's really important that their viewpoints are merged with a lot of the input from members to make sure that we can actually do the things we wish to do. The key thing here is going to be organization, prioritization, and communication of the work as it progresses. And one of the things that's really important is we welcome input. So SEG is your organization. It's ours. It's something that we all value, and we're going to be looking for more input as we go on during this process. SEG 2024 meeting this year was in Namibia. It was a really fantastic meeting. I believe it was the second meeting we had in Africa, one of the first big meetings that we had. Anyone that went to this meeting had an outstanding technical program, great social events, outstanding field trips. And I'd like to thank everyone that took part in this, but special thanks to the organizing committee that was led by Anna Nguno and Lawrence Robb. They led a team of outstanding volunteers that provided a wonderful experience for anyone that went, and thanked them greatly. It was also a year of significant change. I mentioned our conferences are one of the key pillars. One of our businesses, our key business focus is really about content delivery. So our speakers today are an example of that, the annual conferences, but our publications are also a key point of our content delivery and professional development plan. And we've had quite a bit of change this year. A lot of shifts where we have a new editor, David Cook, a new technical editor for SEG Discovery, Regina Baumgartner, and a new director of a new board chair for the publications board, Jens Gutzmer. These three folks have come in with lots of great ideas to build on an already outstanding base of excellence in our various journals, as well as our publications, and look forward to the things that they are going to do in the next few years. And as we bring in new people, people leave. And I'd like to, our flagship journal is Economic Geology, and we've had an outstanding editor at the helm for the last 17 years, Larry Meinert. I'd like to thank Larry for his outstanding service. I had the pleasure to work alongside Larry for a number of years during that period, and it was a very enjoyable experience, and he's led to make sure our journal has maintained its excellence in the field, and it's one of the top publications for our discipline. I'd also like to thank outgoing President Stuart Simmons. Stuart was at the helm at a really challenging time in the organization where there's a lot of uncertainty, and Stuart was really key in ensuring the viability, and will be one of the most material presidents in our history, ensuring that the organization was stable and made it through a very challenging period. He, along with our comptroller, Anna Thoms, as well as a number of SEG staff, really kept the ship afloat during an uncertain time. And I'd like to thank Stuart for his outstanding contributions to SEG long-term, and particularly during his term as president. In my term, I've had the luxury of being able to build on Stuart and others laying a really important foundation and look towards the future. And in doing that, I've had a lot of help from our incoming president, Ann Thompson, as well as Jen Craig and the SEG staff. A lot of what I've done this year has really been in partnership with these folks, and their support during this year has been really exceptional. And I wouldn't be able to do a lot of the things, including the strategic planning, if not for their input. And I'd like to also thank at the end of this, a couple of people beyond this, our speakers today, as well as Beatrice for leading this. This is a great opportunity to celebrate excellence in our field, which is something we're really good at. And I'd like to thank everyone for doing that. And on top of that, the people that have engaged with our organization and maintained the membership, show up to these webinars, go to our conferences. You're our community, and we really value you as members. We hope you stick around, and thank you for continuing to be a member and contributing to our organization. And with that, I'd like to wish you all an outstanding holiday season, and thank you for the opportunity to be president this year in 2024. Okay, thank you.
Thank you, Steve. Thank you very much. Much appreciated the opportunity to be here and being part of this. It was such a nice year for SEG. So many things were done. And talking about the conference, that was a highlight. Conference was fantastic. So thank you. Thank you for your comments. And after you, we're moving to Moira Smith's presentation. So let me share my screen again. Hey, Moira, I can see you now. Just sharing mine now to introduce you, then removing. All right, so now we have Moira Smith from Liberty Gold Corp. Moira is an SEG International Exchange Lecturer, And her talk's title is The Mineral Exploration in Challenging Times. And Moira Smith was until recently the Vice President of Exploration and Geoscience for Liberty Gold Corp, with development areas in properties in Idaho, Utah, and Turkey. And she's now a semi-retired consultant for Liberty Gold, with a focus on the advancement of the Black Pine Carlin type gold oxide deposit in southeastern Idaho, and identifying the next big opportunity for Liberty Gold. Formerly chief geologist, Nevada, for Frontier Gold, Moira was instrumental in the successful advancement of Long Canyon, now an operating gold mine in Nevada. She developed an understanding of geology and controls on mineralization at the Long Canyon, and built the geologic model for ongoing exploration and resource growth. And prior to her to Frontier Gold, she managed exploration programs for Teck on several high-profile advanced state gold and copper gold projects, now operating mines, throughout the Americas, including the Pogo Gold deposit in Alaska, the Cobre Panama copper moly gold porphyry deposit in Panama, and El Limon gold deposit in Mexico. She has a PhD degree in geology from the University of Arizona, and she is a professional geologist. She has held board or executive positions with numerous industry associations, and is a past president of the Society of Economic Geologists in 2021. She was a recipient of the Colin Spence Award from the Association for Mineral Exploration of BC, and is a director of Discovery Metals Corp. So Moira, I can see you now. I'll stop sharing my screen so you'll be able to share yours. Thank you so much for being here.
Let me try and share my screen.
I'll let you know once you're done.
Says your screen sharing is paused.
I can see yours. It's all black now. You're gonna try to cancel and start over, maybe?
Yeah, let me try that again.
Yeah, take your time.
I have to stop share here and start over again.
Yeah, don't worry about it.
Your screen sharing is paused. Well, it worked earlier.
Yeah, that's weird. Let me see if I can find a way to help you. Is your presentation opened already? Is it in presentation mode?
No, it's in, I have to do it in regular mode and then put it in presentation mode.
Oh, all right. Another option is for you to have it presenting already.
Okay, I see it now. Let's try that.
It's still black. Ah, now I can see it. Yeah, it's not in presentation mode yet, but I can see your screen.
Okay, how does that look?
Oh, looks great. Thank you.
Okay.
You're good. Yeah.
So sorry about the delay there. So today I'm going to speak about the future of mineral exploration. I've always been intensely interested in the E part of SEG, and so it talks a lot about economic factors and whatnot. But before I do that, I wanted to say a few words about what I did with my lectureship, which was probably a little bit unorthodox. I'd seen a lot of anecdotal evidence that economic geology presence across geoscience departments, particularly in the US where I'm based, has been declining, with fewer geologists choosing mining as a career. So in part, I targeted universities that had declining or small economic geology presence, partly due to retiring professors being replaced by professors in other earth science disciplines and for other reasons. The most often requested talk this year was on what a career in mining might look like. And I talked to undergraduates and graduate students that were from across the geologic spectrum. My primary messages were, first of all, that you don't have to study economic geology to have a successful career in the mining industry, and that there are multiple career paths across a multitude of disciplines. It's a really big tent, and there's probably room for you in there. And finally, that mining is more relevant now than ever, really, due to the emphasis on critical minerals and the clean, green, new economy. So, and that with a plea to seasoned economic geologists out there with careers in the mining industry, I hope you'll consider heading over to your nearest university or even a secondary school and giving a talk about your career and careers in general in the mining industry. I think students would be really receptive to that and learn a lot. So with my talk here, first I'm going to set the stage and talk about current economic conditions. Things aren't looking that good out there. Then I'm going to do a little segue into some current trends that I think we're seeing in the minerals industry, including things like critical metals, ESG, what seems to be a pivot to copper and silver and other base metals, and new technology. Then I'm going to go back to the depressing stuff, the junior exploration model, and a few comments on how we might get back on track. So first of all, the elephant in the room. We can't ignore that gold mining company stock prices have vastly underperformed the gold price over the last few decades. And this graphic here is showing the comparative performance of the GDX, which is an ETF managed by VanEck. And it has a basket of gold mining companies in it. And looking at that against COMEX gold, the gold price over the last couple decades, you can see that there's huge divergence here. Starting equal, the GDX has vastly underperformed the price of gold. I should note that a lot of these first slides are gold focused, but you can choose your favorite commodity here and things look quite similar. More to the point, gold mining and gold exploration stocks have vastly underperformed the general market over the last decade. And so here I'm showing the GDXJ, which is an ETF which focuses on junior and mid-tier exploration, and plotting that over the last 10 years against the Standard & Poor 500. And even with relatively stellar performance in 2024, both the GDX and the GDXJ are still losing ground to the S&P 500. If you invested in the GDXJ, for example, 10 years ago, you would be flat or underwater after 10 years, whereas you would have seen share appreciation in the Standard & Poor 500 of a couple of 100%. There's a lot of volatility around mining stocks as well, and that scares investors away. So you got to ask the question, why would anyone want to invest in mining related stocks when the returns over the last decade or 2 decades have been so low? And the answer is that maybe you wouldn't. So here we are, just looking at the last 5 years, GDXJ and GDX against the Standard & Poor Spider ETF, and they have vastly underperformed even recently with the rise in the price of gold. And you can see over here changes in gold exchange traded funds, and the outflows have definitely been more than the inflows to this. So then, where do some of the problems originate? Inflation has definitely impacted the mining and exploration industry with increased prices of capital items, consumables, and wages. Now, some of those consumables like diesel have come down since the peak, but it's unlikely that the others will. So inflation has put pressure on mining company profits despite rising or stable metal prices. And this is shown on this diagram where we have all-in sustaining cost to produce an ounce of gold It bottomed in 2016, but it's risen since then, kind of keeping pace with the gold price. So we're not really getting ahead of the game here. And it's worth noting as a corollary here that if you're looking at a PEA, a pre-feas or a feasibility that's over about a year old, it's no longer reliable and should be revised or read with inflation effects in mind, because this all-in sustaining cost has gone up so significantly. Now that translates to mining company profitability. So there's some apples and oranges in this discussion here, but the net profit margin among the 40 largest mining companies in the world is in decline. And that's shown on this graphic here, where things start looking bad about 10 years ago, and they're just getting worse. The net profit for these 40 largest mining companies was about $90 billion in 2023. We haven't seen the 2024 numbers yet, which is just a small fraction of the market cap of larger tech companies. So if we broaden that and look at the 292 mining companies worldwide, the total market cap is about $1.75 trillion, which is only half of a big company, NVIDIA. So it's we're pretty small potatoes, and that's part of the reason also that investors just aren't that interested. If we look at the average price to earnings ratio of gold companies worldwide, as of earlier this year, that PE was about 43 compared to 16 for S&P 500 companies. Another thing of concern is looking at mining company investment in mining operations. And you can see the trend of investment in both sustaining capital and, more importantly, development capital peaked in about 2022 here. And it's been sliding down ever since and is projected to get even smaller out a couple of years. So, return on investment in most mining companies is lackluster. The profit margins are thin. Share prices aren't keeping pace with other sectors. Inflation is not helping at all. They're showing a failure to invest in future growth. And you layer on top of that the overall perception, which has been around forever, but seems to be getting worse, that mining is dirty. And a lot of bad news headlines lately, and you can read the words here, serious misconduct, failed, disaster, it's over. These kinds of news headlines tar everybody with the same brush. So as a result, let's look at the largest gold mining company in the world, and by all measures, we would call them a successful gold mining company, Newmont Corporation. Over the last decade, we've seen a decline in stock price, and even in the last year or so, we've seen some rise in the stock price, but it still is not keeping pace. Some of that isn't their fault, because they get tarred with the same news headlines that we all do, but something isn't working here. Then we look at the junior gold explorers, and they're doing even worse. So there's been a real flight of capital out of this area. If you have cash, chances are you're still exploring it. If you don't, chances are you might be just dead in the water. The price to net asset value for early stage companies is at an all-time low of about 0.2. And the PNAV for developers is about 0.35, which is also low. If you recall in the past, that number would be close to or even over 1. We look at junior and intermediate financings. They peaked in about 2022, post-COVID, and they have been declining ever since. But the number of financings is going up. So that means each company is getting a smaller piece of the pie and making it hard to explore and keep their G&A costs down. Another alarming thing is if we look at exploration budget by stage of development, over on the left here, we see that grassroots exploration is reaching all-time lows. And that's partly because the juniors just don't have enough capital to keep exploring. We also, probably all of you have seen this graphic. Arguably, our track record of discovery is diminishing. This is for gold, and you can see projected gold in new gold in discoveries from a high, up in the 1990s, with a downward trajectory here, even though exploration budgets have gone up over time. So you got to ask yourself, why is that happening? Are surface gold deposits just getting harder to find as time goes on? I honestly don't think so. A lot of older geologists would probably say that we spend too much time in the office on our computers and not enough time in the field. Is that the issue? Well, it might be part of it, but I think the big thing is because exploration companies, by virtue of the fact that they're underfinanced, are spending too much money on G&A and on flogging dead properties. If we look at major copper discoveries from 1990 through that same time period, we see the same decline in copper discoveries with an otherwise increasing exploration budgets. So a little bit of a silver lining here is that the gold price and the price of other metals this year has been relatively healthy, and that is likely to continue into the future. Financial institutions are betting that gold price will be somewhere between $23.50 next year, which frankly would be kind of a disaster, and upwards of $3,000. Here's just a list of the banks and their predictions. Gold price is projected to decline slightly in future years, although usually the banks really have no idea and they tend to project things out based on the current price. We can expect extreme volatility for gold based on the last several years of the data, and certainly in the last few months or even the last day. I don't know if you noticed, but COMEX gold declined something like $50 today. And that volatility is due to factors like inflation, the value of the US dollar, global conflicts, and US interest rates, and political instability and whatnot. In terms of other metals, here's a graphic showing things like aluminum, copper, lead, nickel, tin, and zinc. Metal price forecasts for 2024 in blue, 2025 in red, and 2026 in yellow. And things are fairly stable across the board. There was a fair bit of volatility this year, but again, the banks tend to just project things out in the future, so we're not seeing necessarily a huge change. It is worth noting, though, that strong demand is forecast long-term in industrial metals. This graphic is often shown around showing gradually declining copper production due to a lack of replacement of reserves, but the demand is going to continue to climb gradually over time, leading to a potential shortfall, and hopefully that means higher copper prices and more exploration. You can see over on the right here, industrial metal inventories across the basket of commodities showing almost an all-time low in 2023. So that also bodes well for metal prices and hopefully exploration. So I wanted to talk about some current trends here, and starting with critical metals and minerals. And for anyone who saw Reimar's excellent presentation at the beginning of this seminar, he did a much better job than I did in his first 10 minutes in kind of summarizing what that industry looks like. But suffice it to say that enormous quantities of minerals are going to need to be mined from across the periodic table of elements, and that will fuel the green economy, including batteries and solar panels, electronics, etc., and even more mundane elements like copper needed for cars and transmission lines and whatnot. So the demand for these will be tied partly to the rate at which the green transition takes place. But conversely, the rate at which it takes place might be partially determined by the supply of these same metals and minerals. Either way, this ramp up of demand is not going to happen overnight, and that might leave some early investors and explorers in this sector disappointed by lackluster or erratic share performance, and we're certainly seeing that. Prices for metals with low consumption can be strongly affected by the activities of countries with access to those metals, and a good example of China, which controls the lithium, REEs, and a lot of other of these metals. And it's worth noting that these countries don't always have our best interests in mind. So in terms of it's not going to happen overnight, there's some great reports out there, one by the World Bank a couple of years ago that summarized all this stuff. The first graph here is showing energy storage over time, and that would be in grid storage and automotive. And you can see that they have three scenarios here, kind of a low-end case, their best guess case, if you will, and a high-end case. So that amount of demand really is dependent on, or that amount of supply is definitely dependent on demand. This Reimar showed this graphic on the right here already. It's 2050 annual demand for various commodities as a percentage of 2018. And you can see some of these are up hundreds of percent, and even the ones that are more like 5%. Some of these, like copper, that's an enormous amount of metal. So either way, it's going to happen, but it might take a while. So just to look at the exploration for lithium, for example, the market reacted favorably when a bunch of junior companies fled like gold exploration and rebranded as lithium explorers. But then last year, the price of lithium crashed and the value of those companies crashed as well. So in Nevada, where I'm based, there was a huge amount of staking in the southwest part of the state. Those black dots are showing placer claims related to lithium brine exploration. I might note that in Nevada, there's two kinds of lithium that are being explored for: lithium brine, where we already have an operating mine, and lithium and clay, where we're about to have an operating mine. But if you look at the companies that are that stake those claims and are purportedly doing exploration, you'll see there's a few healthy ones at the top of the list, but most of these companies have a market cap of maybe $1 million to $5 million. So you know that they're not actively doing exploration or are really equipped to do it. Nevertheless, total battery metals exploration in terms of budget has reached an all-time high in 2023. Numbers aren't out for 2024 yet. And here we're showing nickel, lithium, and cobalt exploration. However, it will be interesting to see what that chart looks like after 2024. And that's because the price of those metals and a lot of others crashed in late 2023 and came down to earth. So this is showing lithium price for the last 5 years. This only goes to January 2024, but things have bumped along the bottom here for the rest of the year. Same with cobalt, where a mine in Idaho was halted their build of the mine. Moly prices, nickel prices all look about the same. So price volatility can make exploration and mining a really risky bet. And finding a buyer is not as easy as selling on the LME. A lot of battery metals have complicated metallurgical properties, and let's face it, countries that control the supply control the price. So looking at lithium miners in general, this is a lot of ETFs have come out in the last couple of years to track miners of various critical metals. This one is for lithium, and it was started in June 2023, and you can see if you invested $10,000 in this fund in 2023, that's worth $4,000 now. So across the board, lithium miners are not doing very well, and part of that is because China controls about 70% of the world's lithium production in China and elsewhere, like places like Zimbabwe, and hence they control the price. And right now, they're actively forcing a lot of operations underwater. Looking at one specific example, Lithium Americas Corp is developing the largest lithium mine in North America in Northwest Nevada. It's clay-hosted mineralization called Thayer Pass. It's currently under construction. They have loans from the US DOE amounting to over $2 billion. They have a JV with General Motors with an offtake agreement to sell their product, and they are still encountering headwinds with the stock price. So this is kind of what the situation is realistically with explorers and miners. Another current trend appears to be a pivot to silver and base metals. There is renewed interest, I think, in silver, copper, and other base metals. And what we see here is a graphic showing exploration budgets worldwide for commodities such as gold and copper and other commodities. So it's showing a decline in money being put into gold exploration and a rise in money being put into other commodities. And this graphic on the right showing just the change from 2022 to 2023. The exploration space seems to be healthier here. So here's a Sprott Junior Miners ETF with mostly explorers and small producers. And you can see this was started in April and has actually shown an increase in price over time, suggesting that collectively companies are doing a little better than they are in the gold space. Silver is very volatile and very much, the companies are very much leveraged to the price of silver. So here's silver producers on the right, a lot of volatility, and that's reflected in this Junior Silver Miners ETF I'm showing on the left over the same time period. And I'm hoping that things really start to pick up with the junior miners, given the recent rise in silver price. Another trend I wanted to talk about is the rise and unfortunately the possible fall of things like DEI and ESG. DEI, otherwise known as diversity, equity, inclusion, is a policy that's critical to the functioning of public companies, and in some cases is the law, or at least a very strong suggestion, and it encompasses things like the board composition of public companies. Just showing the Toronto Stock Exchange here, you don't need to read all this, but the rate at which women are being appointed to boards, the number of board seats, etc., are definitely on the rise. And that's a good thing to get underrepresented people into various roles throughout the mining industry, not just on boards. But I think we still have a long way to go to eliminate systemic barriers to advancement among these groups. Unfortunately, there's a lot of backlash against DEI these days, at least in the US, and a recent US Supreme Court ruling against affirmative action in university admissions highlights this backlash against DEI. And there's certainly an anti-DEI sentiment among the incoming administration in the US. So I do fear that some gains along these lines will be lost over the next while. ESG, or environmental, social, and governance, these policies have been advanced in recent years. And it's been shown repeatedly that it is in the companies' and shareholders' best interest to advance these policies, particularly in the mining space. In the mining space, it helps facilitate a company's social license to operate, both on a local and global level. And it also helps facilitate a company's access to capital. And that's because a lot of banks that, lend money are forcing companies to adhere to international standards. The Equator Principles is one example of these international standards. For companies to comply with this, it's definitely not a cheap date, but it's absolutely necessary for permitting an operation. So I think people will just get used to this, and it'll be the standard going forward. Then I wanted to talk about trends in new technology. I could fill an entire afternoon with this, but I'll just touch on some of the highlights. The first one is AI, of course. A lot of us hear this, but we don't exactly know what it is. So simply stated, for the exploration space, it's supervised learning. So these algorithms learn from data sets where we have both the input features like geophysical, geochemical, and structural data, and the outputs, that being the presence or absence of mineralization, the distribution of mineralization, and etc., are known and provided. So the algorithm learns that relationship between input and output, and then it can make predictions on new data sets where the output, namely the presence or absence of a deposit, is not yet known. It goes without saying that data quality here is absolutely paramount, and that human input is essential. This is never going to replace us. So we have evaluation of very large data sets. A question I would have is whether pattern recognition, can it do it better than humans? Maybe. But for sure, we have better targeting, leading to cost savings in field work and drilling, because this approach can eliminate a lot of areas where we don't really need to go or need to drill. It's also being used in data-rich environments for targeted infill drilling, resource and reserve definition, grade control, and mine planning. I've seen it used very successfully for reserve definition at a mine in Ghana. It also targets mine operations efficiencies, particularly around autonomous systems and intelligent mining. And I think there's no doubt that it's here to stay in mining. This interesting graphic over here is from a paper on implementation of AI in mining applications, and it shows about 3/4 of and this is based on citations in published articles. About 3/4 of them deal with the mining space, shown in orange, about 15% or so in mineral exploration, and the rest in reclamation. If we look at a graphic from the same paper by Azari et al., looking at mining related publications distributed by year, you can see there wasn't much going on until about 2018 or so, and then there's been an exponential rise. So clearly AI is becoming more established in the mining space. Another piece of new technology is drones. They've been around for a while, but they're getting larger, they're more reliable and more sophisticated, and can carry heavier payloads. They've been used to create orthophotos and digital elevation models for quite a while, but with the heavier payloads, they are starting to do magnetic surveys, LiDAR surveys, and etc. They're certainly cheaper and safer than helicopter surveys. They're faster than ground surveying. And what's great is they're suitable for smaller properties and smaller budgets. So I would say at this point, there's absolutely no excuse for having a bad base map. And then in mining, drones are used to inspect and map open pit and underground workings, unsafe areas, and are used to create virtual reality environments. Another trend we're seeing, especially over the last couple of years, is do-it-yourself resource estimation. This could be a little dangerous, but if we use it properly, it's fantastic. We now have relatively affordable software for 3D modeling, resource estimation, and even building block models. This software, I'm using Leapfrog Edge as an example, but there are others, has advanced wireframing capabilities, can do dynamic anisotropy, and it produces exports that are compatible with mine planning software. I really believe that this in-house modeling capabilities, and yes, you do have to develop your staff to be able to operate this, they reduce the guesswork, allow for continuous upgrades to the geologic and resource model, so you're not going to get a bad surprise when you hand everything over to your independent estimator. This graphic is from Black Pine property that I'm very familiar with, and there's no way we would do exploration without this capability. Geophysical advances, this isn't a topic that could take hours, so I'm just going to touch on it. There's now 3D inversions available for just about anything, including gravity, mag, IP, CSAMT, and etc. And this is widely available and in wide use. There's also better sensors and better software and etc. So it's really becoming a valuable tool. It's always been a valuable tool, but more so now than ever. Seismic is on the rise in exploration and mining. A lot of this is out of reach to companies that don't have large budgets, but it's worth mentioning. And I've just put one example here of Ivanhoe's Typhoon 3D IP program. They are using it in joint venture with companies all over the world now and looking for deep sulfide mineralization. Then we have downhole and borehole systems. Core scanning, be it hyperspectral, XRF, magnetic photos, etc., has really become established in the mining industry. You can do it on site if you can afford the setup, or send your samples off to the lab. It's certainly better than the human eye in identifying and quantifying alteration. So it really takes the guesswork out of things. You just can't get this kind of data from looking at a rock. Do I think it'll replace a human being as far as logging core? No, but I think it can be very helpful and worthwhile. There's also downhole and borehole systems. Just one example are optical and acoustic surveys that can be used for geotechnical work. Compared to oriented core, particularly if you have broken rock, it's faster, it's potentially cheaper, and it's much, much more reliable than trying to orient core and having humans take those measurements. Last example here is photon assay. This is really cool, and it's just come into its own in the last few years. This is a method that uses non-destructive high energy X-rays for assaying for gold. And at this point, silver and copper are also being assayed for. It uses a larger sample size. It's independent of the mineralogy of the sample, which can give you trouble with conventional assaying. The sample prep is really easy. The sample is only crushed. It doesn't have to be pulped. It doesn't have to be dissolved or anything like that. And this reduces the risk of sample cross-contamination and lab mix-ups, which are, as everyone knows, are almost unavoidable. It's really fast, and it's starting to be employed by mine sites around the world and offered by commercial labs. I've seen it in action in Ghana, and I'm really impressed with this, and I expect that the use of this system will just continue to grow. So the bottom line here, in my view, is that there isn't that much that is truly new under the sun, but the same principles and techniques we've been using for a long time, like hyperspectral, mag, EM, etc., are still the foundation for exploration, but advances in technology can do it better. It can do it faster, more efficiently, cheaper, and allows for collection and integration of very large data sets. So, question for you is, how many of these new technologies are you using? And if not, why not? And now I'm going to go back to kind of where I started, looking at the doom and gloom of the economics of mineral exploration. And I wanted to talk about the junior mining model, something I'm very familiar with. What I'm showing here is called the wealth creation scenario, the Lassonde curve. Most of you have probably seen this, and it shows relative valuation of a company and or its stock over a given time frame, usually a decade or two, if you make it all the way to the first pour, for example, in a gold property. And you start out at a low valuation, drill some holes, make a discovery, keep drilling it. The price of your valuation of your company goes up and up. Then you reach about a first resource. Then the really expensive stuff like engineering studies kick in, and you work and finance and then put it into development. And hopefully the valuation of your company goes back up and reaches a high right around the time your mine is commissioned. Excuse me. However, this is probably 1 out of 100 or even 1 out of 1,000 thing. You almost never see a junior company go from 0 to 100, and lots of other things get in the way. So here are my own curves. Here's what used to happen, but rarely happens now. We start a new company, get some awesome drill results, keep drilling, the valuation of the company goes up and up till we get about to a resource estimate. And then a major company swoops in, takes the company off your hands at a high valuation, and it's a win-win for everyone. Unfortunately, that hardly ever happens anymore because the mining companies have learned that if they just keep watching that your junior company is going to go down the Lassonde curve into the valley of death here through more dilutive financings and a lot of expensive de-risking, and they can come in down here and take the company out just as easily. They buy a more de-risk company and they pay less for it. So here is what tends to happen. We go through the first part of the curve and we do a resource estimate. Nobody buys us. We finance. We do a preliminary economic assessment. We finance again, maybe put it into pre-fees. And then when we're looking for development capital, we can't get any. And by then our company has gone down to a really low valuation, or our shares anyway. And we just kind of bump along the bottom here. And that's kind of the end of things. Now this is a great opportunity for a major or a mid-tier to pay a little bit more and take out a de-risked asset for cheap. But if your asset is something that a major or a mid-tier doesn't want, you're kind of stuck. Another wealth destruction scenario is I call boom times and busts. That's where people start a new company around a low quality asset. They get founder's stock for 5 cents, and then they finance at a very high valuation. And then they twin some holes. A lot of the early people are going to get out at the top here, but then they twin some holes, they drill a few more holes, and then they're out of cash. And then they do a series of dilutive financings for no real gain, and they enter what I would call the zombie phase. And that's what happens to probably the majority of junior companies out there. This is certainly not sustainable over the long term. It's a total waste of investor capital. So at this point in time, and you can see that reflected on the GDXJ valuation, which is some of the best companies, most explorers are nearing that zombie status or have at least severely curtailed their exploration. The return on investment in junior explorers is terrible. You know, there's 3,000 public companies worldwide, and the vast majority don't produce a quality asset for sale or for development. And that track record is getting worse. So you got to ask yourself, how many companies actually have potential tier 1 or tier 2 assets that would appeal to what amounts to fewer and fewer major mining companies, thanks to mergers and acquisitions. They're only getting larger, so they're looking for larger and larger assets. So if you're not familiar with that term, a tier 1 gold asset, for example, there would be an equivalent in other commodities. It's an asset with reserve potential to have at least a 10-year mine life, annual production of 500,000 ounces, and cash costs that are in the lower part of the industry cost curve. That's according to Barrick, but this metric is pretty widely used. If you think about it, a 5 million ounce reserve, you probably need 8 or 10 million ounces of resource to get to that reserve number. So that is a very big deposit, and one should be able to recognize fairly early on whether you have it. So then if they do have it, how many of them can raise that $50 or $100 million required to advance a property through feasibility, or even enough money to do meaningful exploration? So here's a company, a zombie company. It had a higher valuation in the past, and then it just kind of bumped down so that it's trading at half a cent now. And there are a lot of companies out there that look like that. So part of this is systemic. I think that the public junior exploration company model is basically broken. It rewards early investors if they can get in at the beginning for cheap and get out fast. It rewards companies for good drill holes, but not for the hard work it takes to make a deposit or mine. Maybe it did in the past, but it's certainly, it's rare now. It relies on fickle investors who can put their money anywhere and probably should. It conspires with bank analysts who literally never say to sell a stock, paid pumpers and shady newsletter writers who inflate the value of a stock so that the only way after that is down. It enables companies that are started at the top of the market around marginal properties that'll never be mined. It enables zombie companies that exist for years and years only to raise like $500,000 a year, which just pays corporate salaries and holding costs and puts no money into the ground. It enables spin out of marginal properties into new companies so that you have twice as many corporate salaries spread over the same marginal properties, and all your money going to G&A costs. And let's face it, these companies are structured the longer they last to eventually blow up with too many shares out, because for many people, issuing shares is the only way to raise capital. So with the last few slides, what can we do to get back on track? So good companies, in my view, have well-seasoned management teams, a management track record of success in financing and M&A and development, management success and discovery of economic deposits, access to capital, and potentially other means to finance meaningful exploration. They try and keep their share structure tight. They do exploration in promising districts. They have assets with size and a clear path to tier 1 or tier 2 status. The companies are advancing engineering studies, earning their social license, and permitting while exploring. If all junior companies had most of these characteristics, there would be a lot fewer companies and more capital to allocate to individual companies. So as junior explorers, we should all try and emulate the good companies, not start so many companies, kill the zombie companies, drill and kill marginal properties instead of hanging on to them, carry out better due diligence around acquisitions, investigate non-dilutive financing options, and maybe we need the government to step in here. Maybe governments should start stockpiling of critical minerals to decrease price volatility. We certainly do that with gold, with central bank buying. Why not some of these other commodities that we desperately need? If we can't police ourselves, I wonder if more regulation or oversight is needed. Geologists and technical disclosure are already regulated in a lot of countries, so how about minimum qualifications for CEOs? Just an example of one of the things on the list, acquisition targets. We need to do better due diligence, and we need to continue other factors besides the cool rocks. So for an acquisition target, I look at a low-cost entry point, low-risk jurisdiction, security of tenure, transparent permitting, good access and infrastructure, environmental considerations, access to water, what do the stakeholders look like that live around it, looking for deposits with a deposit model that has multiple big operating mines, a clear path to a tier 1 or tier 2 deposit, simple metallurgy, and low-cost mining methods, or at least high grade. So one thing I hear from a lot of people when I discuss these things is, well, I'm just a geologist. What am I supposed to do? I think as exploration geologists, we can all embrace new, better, and more efficient technology. We can understand the business aspects of the company that we're working for. And a really good start is that drill, deal, or drop course that's offered by Michael Doggett and Ken Lay, and exclusive to SEG. You can learn a lot about the industry. We can work for companies that are well-financed, have great properties, and a good relationship between management and technical staff. You don't have to take the first job that comes along. Take a good one. If you're relatively new to this, consider working for a major mining company first to understand what a mine looks like and the steps that are needed to get there. It's quite shocking. We should also pledge to work only on the best properties with a clear shot at being mines. We should pledge to drill and kill marginal targets. And I hope that we can all suit our souls and stand up for the truth. If you think about it, geologists know the most about the asset that we're exploring, and they're the ones that need to tell management that they're drilling holes into a dog and that we need to move on. That will be the first line of defense against wasteful spending and wealth destruction. So that concludes my talk. I'm sure that no one necessarily agrees with me on everything here, but hopefully it will spur some interesting discussion. Thank you very much.
Thank you, Moira. That was fantastic. Especially for early career students, like me, for example, and many others that are here with us right now, they even smaller potatoes. So thank you so much for your advices and for your presentations. And we have some questions for you. I'm just sharing my screen before it. Here, there we go. Can you see it?
I can.
You can? You can't?
Yes, it's good.
Yeah, thank you. Yes, thank you so much. So the first question is, with all the concerns related to the industry at the moment, how would you address the student space with regards to geoscience students who are interested in getting involved with the industry? What positives could they focus on looking forward?
Well, yeah, there were some negative things in this talk. The positives, and I've talked to lots and lots of students about careers this year. It's one of the most rewarding careers that you will ever get into. If you work in the field, particularly, you're working with a close team, you make lifelong friends. That's one of the most important things. I learned you'll see new countries, meet new people. But even if you are not a field-based person, there are lots of other things you can go into. You can sit behind a computer, and if that's your thing, and do ore reserve calculations. You can go into the engineering side of things. You can save the world by going into the environmental and permitting aspects of of it. And you can do all that without a degree strictly in economic geology. There will always be a need for metals, thus there will always be a need for geologists in this industry. That being said, you might have some ups and downs and bumps in your career. Over.
Thank you. Any thoughts on addressing challenges with identifying talents?
Identifying what?
Talents?
Identifying talent. That's a good question. If I am looking at somebody's resume, I'm going to focus on how broad their education is. I'm going to look at, have they stepped outside of geology and taken a GIS course, and because I'm going to need that. Are they familiar with 3D modeling? That's not strictly raw talent there, but I think raw talent comes from actually talking face to face with people. So I strongly encourage everybody, if they have an opportunity at a meeting or something like that, to go out and introduce yourself to people and network. And I can't stress that enough. The recent meeting in Namibia was a great example of networking opportunities, and I was thrilled to see that so many people take advantage of them. That's how you get your talent on display.
Yeah, perfect. Thank you. And we have a comment in here. Thank you for your nice presentation. It was very insightful. What a great session. You asked about which technologies in the mineral exploration is being used, and I will tell you, for me, none of them. Unfortunately, we don't have any of the tools in our university. I'm from the Kurdistan region, northeast of Iraq, and we got a lot of struggle in the exploration. So a hard scenario, that's a comment.
I would feel your pain. I think a lot of these new technologies I talked about are mainly in use in the exploration industry, with the exception of some of these geophysical things and a core scan and whatnot. I think the best way to get exposure to those is to talk to mining companies, see if you can get a master's degree set up or something, in partnership with a company, and then you can take advantage of what they have to offer.
All right, thank you so much. There are some other questions for you, but feel free to type them. I have one for you as well, but I'll type it, so because we don't have time to keep going here. But Moira, thank you so much for being here. Very insightful lecture. Thank you, really.
Thank you. That was a lot of fun.
So now we are moving to our next presentation. Let me pass my slide in here. There we go. All right, so our next lecture is Adam Simon from the University of Michigan. And Adam is an SEG Distinguished Lecturer. So Adam Simon is the Arthur Turner Professor of Earth and Environmental Sciences at the University of Michigan, the USA. He earned degrees in geology and geochemistry from the University of Maryland and Stony Brook University, and was a postdoctoral fellow at the Johns Hopkins University. His scholarly work focuses on the global flow of energy and mineral resources, with an emphasis on the geologic availability of energy-critical metals. Adam has co-authored two textbooks, Mineral Resources, Economics and the Environment, and Earth Materials, Components of a Diverse Planet, and published 100 papers in the field of energy and mineral resources. Adam has done research and given invited lectures on all 7 continents, including a TED Talk in 2022, and was awarded the University of Michigan Provost Teaching Innovation Prize for his transdisciplinary pedagogy. So Adam's talk title is The Relationship Between Mineral Production and Human Development. So I now invite Adam to join us. Adam, you there?
Hi, Beatrice. Yep, I'm here.
Oh, nice to see you. Nice to see you again.
Nice to see you.
Yeah, I can see you. Whenever you're ready, you might share your
Yep.
screen.
Share my screen. I think this is right. Yep, you can see my slide.
I can see it. I can see a web page. Yeah, it looks great.
Okay.
Thank you.
All right. So my talk, the earlier talks have been great, and I'm going to switch gears a little bit, and I'm going to focus on the relationship between what you see here and copper. So here we're looking at the world at night. So this is a stitched together compilation of NASA images taken from the space station. And what I want your eyes to see is, in essence, areas of the world such as North America, the United States and Canada on the left, the European Union, parts of the Middle East, parts of India and Asia, where we see lots of light. And we can zoom in on certain areas. For example, here we're looking at Egypt and the Middle East across into Pakistan. And what you're looking at here is the Mediterranean Sea at the top. And then all of the lights here, let me switch this. All of these lights here on the Nile River are fishing boats. And so what we're looking at here are boats with lights illuminated at night, people fishing. And then we can look at Saudi Arabia here, and we can see Medina and Mecca and Riyadh. We can see Bahrain over here. We can see Kuwait and Kuwait City. We can see the United Arab Emirates here. We can see Muscat in Oman over here. If we look now at this area of the world, this is an area where the bottom center is the Republic of Korea, or South Korea. And you can see the city of Seoul here with about 20 million people. It glows at night because of all the lights that are on. Southeastern Korea here, we've got Busan, which is a major shipping port, and then we go across to Japan. And notice the difference here between South Korea and North Korea. That's a really stark difference between lots of light in South Korea and essentially no light in North Korea, where to the top here, what we're looking at are cities in China. We can expand out and look at Asia, where we again see center right, we see South Korea and North Korea and the stark divide. We see Japan illuminated at night with all of its cities. We see most of the eastern half of China illuminated here, Taiwan off the east coast of China. We can see parts here of India that are illuminated. And then we look at Africa. So Africa now has 1.5 billion people. And if we look at Africa, again here, top right, we see the Nile River and all the fishing boats. And then we see Alexandria and Cairo here that are lit up. We see some cities here along the Mediterranean coast of North Africa. We see some cities here in Southern Africa. So here we're looking at the major mining centers in South Africa here in the Witwatersrand Basin. And then we can see some cities here along the west coast of Africa. We can see Accra, Ghana. We can see capitals of Togo. We can see Nigeria. In 2100, so the end of this century, Africa's predicted to have a population of 3.9 billion people. So when we look at Africa and we look at the lack of light at night compared to places in Asia and South Korea and the Middle East, what we look at is a huge potential for natural resources. When we think about energy, this is a plot showing energy consumption per capita or per person on the y-axis, where all of the primary energy that each person consumes is calculated as kilowatt hours. So this is our per person kilowatt hours of consumption every single year for all forms of energy. And what we can see is from 1965 on the left through 2023 on the right, We can categorize countries as high income, upper middle income, lower middle income, and low income. And this categorization is done by the World Bank based on gross domestic income per person per year. And I'm not going to go into those details. All I want to highlight here is that when we look at images of our world at night, what we're really looking at is we're looking at a tremendous difference in the overall economic quality or economic opportunity of a country. So in high income countries, the average person per year uses about 55,000 kilowatt hours versus a low income country. This could be the Democratic Republic of the Congo is one example. And in that country, they're using about 1,000 kilowatt hours per person per year. So there's an incredible gap in access to energy. And we can look here at how access to energy has changed for different countries around the world, where here we're looking at the United States top, Chile, South Korea, China, and India. And look what happens to each of these countries over the last 60 years. So 60 years ago, each of these countries, the United States already had a very high access to energy, about 75,000 kilowatt hours per person per year. All of these countries here, Chile, South Korea, China, and India, were below 10,000 kilowatt hours per person per year. So this is roughly an order of magnitude or a factor of 10 difference. And over the last 60 years, this is what has happened to South Korea and other countries such as China. I put Brazil in here. And so what we're looking at here in terms of access to energy over the last 60 years from 1965 through today is we're looking at human development. So if we take a country such as South Korea, 60 years ago, the average per capita energy consumption per year was a few thousand kilowatt hours. Now the average per person energy consumption per year is about 65,000 kilowatt hours. So that's an increase of at least a factor of 20 over the last 60 years. Similarly, we see China, we see Brazil, and then we see these countries down here on the lower right. India, 1.4 billion people, Bangladesh, Nigeria has a population that's predicted to grow to 400 million people by the year 2100, and the Democratic Republic of Congo down here as well, which has a population that's predicted to double over the next 100 years. Now, when we think about access to energy, if we look again at our world at night, where we can see what some people would describe as the haves, lots of energy consumption in the United States and Canada, European Union, some parts of the Middle East, some parts of India, but very little, and then parts of East Asia. We can correlate access to energy with human development. And we do this by calculating what we call the Human Development Index. And this is an index that scales from 0 to 1, and it's based on 3 metrics. It's based on how long the average person lives in a given country. So what is the life expectancy of a country? How educated is the population? So for every adult age 25 and older in a country, how many years of school did they complete? And for every new baby born in the country, how many years of school do we expect them to complete by the time they become an adult? And then this third is a decent standard of living, where we use gross national income as a standard of living. So we take these 3 metrics that we can measure, and we calculate the Human Development Index, and we scale it so that values fall between 0 and 1. And globally, if we look at all countries where the colors correspond to the Human Development Index, again, life expectancy, how educated the population is, and what the gross national income is per person in the country, we can see that most of Africa in 1990 had low values of Human Development Index. We have countries such as the United States and Canada, Australia, New Zealand, Japan had very high Human Development Index scores. Some countries in Europe also had very high scores above 0.9. And look what happens from 1990 to today. We see a lot of change for some countries. So we see, for example, if you look at China and if you look at South Korea, we can see that there was a lot of change in those countries over the last 60 years. So life expectancy is getting longer. The educational attainment of the average person in each of these countries is getting longer. But we still see a lot of countries here, Afghanistan, Pakistan, India, other parts of Southeast Asia. We see lots of countries in Africa that still have Human Development Index scores that are much lower than other countries around the world. So here, if we compare some of the Human Development Index scores or values, China is 0.788. South Korea or Republic of Korea is 0.929. Japan's 0.920. The US and Canada are both about 0.93. Chile and South America is 0.86. And then we have the DRC is 0.48. So there's a tremendous difference between the human development, level of human development in the DRC and most of the other countries in Africa with respect to what we classify as high-income countries, and in the case of China, upper middle-income countries. Now, this is a plot where we're looking at the y-axis is the Human Development Index. So again, a value that approaches 1, that's an indication of very high life expectancy, high number of years of schooling, and high gross national income per person. And what we can see here in black, the black are high income countries. And so I've highlighted here Switzerland and Norway and Chile, which are high income countries. And then of course, all of these countries here are classified as high income countries, including South Korea, the United States, Canada, Saudi Arabia. And then we have in yellow, the squares, China. These are upper middle income countries. And then we have the black triangles here are lower middle income countries. And among the lower middle income countries, we have India and Nigeria. And then the gray circles are low income countries here. And I'll highlight the Democratic Republic of the Congo, or often referred to as the DRC here on the lower left. So what we can do is correlate the level of human development with respect to energy consumption measured in kilowatt hours per person on the x-axis. And there are a couple of things I want to highlight. One is that it's clear that increasing levels of human development are correlated, and most would say caused, by higher energy consumption per person. So going from the human development in the Democratic Republic of the Congo to the human development in Chile requires an increase in the per capita energy consumption. The good news is that if we look at all of our high-income countries here in black at the top, what we can see is that having higher levels of human development does not require having very high levels of energy consumption. And I'm not going to go into the details about why all of these countries to the right have such high energy consumption, but just to make the point that increasing the level of human development from low income to high income countries requires increasing energy consumption per capita. Now, if we look at the same plot, again, here's Human Development Index on the y-axis versus gross domestic product per capita. What we can see here for the countries identified as Chile and South Korea is that from 1990 here to 2024, what we see in both of these countries is an increase in economic output per person measured by GDP per capita and an increase in human development. So both Chile and South Korea moved from HDI values of about 0.7 to HDI values for Chile that are approaching 0.9, and for South Korea are greater than 0.9 today. So human development requires capital. If we then blow this up, so we're looking at energy use per capita versus GDP, just to highlight again, Chile's human development increased, economic productivity increased. South Korea's human development index increased, economic productivity increased. And we see this if we look at, in this case, Santiago then and Santiago now. So the photograph on the top is Santiago, Chile in 1900. There are no skyscrapers. You can see the Andes Mountains in the background, and Santiago was a relatively small city. Compare Santiago in 1900 with Santiago today, and we still see the Andes in the background, but now we see the phenomenal growth of Santiago over only about the last 60 to 70 years. And here is where we can introduce the relationship between economic growth, human development improvement, and copper. So on the lower left, over the time period from 1960 on the left to 2030, projected out into the future, 2032 on the right, what we're looking at in black is the production of copper for all Chilean copper mines over this 65-year period of time. And then projected out into the future up here on the top right are the reported copper production from all mining companies currently operating in Chile. So if we look at, for example, Codelco and BHP and Teck and other operators of copper mines in Chile, what they have reported is over the next decade, they anticipate peaking in copper production and then seeing a slight decline in copper production. So over the last 60 years, copper production has increased year over year, almost year over year, every year in Chile. But now, and we can correlate that in green to gross domestic product per capita. So in Chile, there is an almost perfect correlation and a cause effect between copper production increasing and economic output increasing. Similarly, we can look at South Korea here, where the image on the top right is what Seoul, South Korea looked like in 1900, and the image on the lower right is what Seoul, South Korea looks like now. So from then to now, how has South Korea developed economically? We can look at copper imports. Korea does not have any operating copper mines. So this is a graph that shows copper imports on the left in millions of tons. And what we can see here in black is we can see a significant increase in only the last roughly 35 to 40 years, a significant increase in copper imports. Now, importantly, in South Korea, this copper is used for two things. One, it's used for development, so it's part of the built environment that we see in the image lower right. And two, it's used to manufacture technologies that are exported to other countries around the world. And it's the export of those technologies that we can see in green here have contributed to the very rapid and significant increase in gross domestic product per capita for South Korea. So in Chile, what we see is mined copper led to increasing economic output and human development. And in South Korea, imported copper that was used to manufacture technologies led to rapid, significant growth in economic output, which also led to improved human development. So we can start to put together a picture that correlates copper use, human development, and economic productivity. So now I want to focus on the United States for the next bit of the talk. So if we look at the United States, we glow really brightly at night. And if we look at the US over the last several hundred years, the image on the right is New York City. So this is Manhattan in 2024 with the new One World Trade Center here that's the tallest building. So this is Manhattan today. And on the left is an artistic rendering of what Manhattan looked like in the year 1500 before European colonization. So just visually, there has been a phenomenal amount of growth in all possible ways from the United States then to the United States now. And when we look at the United States now, we can actually determine how much copper is physically embedded within our built environment. So what I'm going to show you on the next few slides are data for the amount of copper that is physically embedded in infrastructure in the United States. And we refer to this as the copper in use stock. It's measured in kilograms per capita. So for every person in the United States, how many kilograms of copper are used every year to build infrastructure? And I'm showing you these data from 1900 on the left through 2000 on the right. So a full 100 years of development in the United States. So first we can look at plumbing. So plumbing, copper is fundamental to plumbing. And this is plumbing that is both bringing in clean water into buildings and homes, and it's also copper used in plumbing to handle wastewater. So if we look at the blue curve here, this shows us the growth in copper use every year physically embedded in plumbing. We can look at wiring. So all of the buildings in the United States, all the houses and businesses, they all have copper wiring that helps move current, electricity within the buildings. We also have copper that's used to generate electricity, to distribute electricity, and to store electricity. So we can look at how much copper is physically embedded in wiring in the United States. We then have copper in domestic equipment in green. So if we think about all of the appliances that are now considered normal in most kitchens in the United States, that's shown here in green. We then have the amount of copper shown here at the bottom in gray for air conditioning and refrigeration. We have copper here in industrial equipment, and here is where we see a change. So if we look at plumbing, wiring, domestic equipment, air conditioning, and refrigeration, what we see over the last century is in general increases throughout the century. But when we look at copper in industrial equipment, what we see is relatively rapid growth up until about 1940, where there's a change in slope, and the wartime effort in the United States from 1941 to 1945, we see really high copper demand or copper in-stock use growing for industrial equipment. And then what we see here with the decline in copper in-stock use for industrial equipment is essentially the offshoring of industrial activity. Similarly, in red, this is copper used for non-automobile transportation. So what we're looking at here are, for example, every United States city through World War II had streetcars. And these streetcars or trolleys all used electricity in order to propel or move the streetcars. And we see tremendous growth in the in-stock use of copper from 1900 through about 1930 when it plateaus. We see a slight increase in the 1950s. And then starting about 1955 to 1960, what we see is almost all of the streetcars in the United States were landfilled or were recycled, because this is when we see the growth of Americans driving. And so what we see in the United States since about 1960 to 1970 is we see a tremendous growth in the number of motor vehicles. So in the United States in the year 1900, there were 8,000 registered vehicles. In the year 2024, there are 300 million vehicles in the United States. So we go from 8,000 to 300 million. And the reason we see the amount of copper embedded in cars increasing starting in the 1960s and 1970s is within a car, we're normally used to thinking of it as having an internal combustion engine. But cars also contain a phenomenal amount of copper wiring that is connected not only from the battery to the starter, to the alternator, to the generator, but all of the copper wiring that's connected to all of the sensors throughout cars has continually increased year over year. So when we put it all together for the United States, what we end up with is shown here in black, where we're looking at a total of about 238 kilograms of copper per person physically embedded in the environment. And we can correlate all of this copper physically embedded in the environment with human development. And so that's now, I've plotted that here in blue. So if we look at the blue and we compare it to the amount of copper physically embedded in the built environment, what we see is life expectancy almost systematically over the last half century, and certainly since 1900, life expectancy has increased year over year. So that life expectancy in the United States, shown here on the right, if you were born in the year 1900 in the United States, your life expectancy was about 50. If you're born in the United States in 2024, your life expectancy now is about 76 to 77 years. So we've increased life expectancy by about 50% over the last century. And one can easily suggest that increasing life expectancy, which is part of improving human development, is directly related to all of the infrastructure that has reduced child mortality, reduced maternal mortality, improved access to medicine and healthcare, improved access to food, and generally higher calorie, better quality food. And so we can correlate copper with life expectancy and other aspects of human development. And we can break that out, as I showed, into plumbing and wiring and air conditioning and refrigeration, industrial equipment, domestic equipment, motor vehicles. We can also look at rail and shipping and aircraft. And we end up with 238 kilograms of copper per American physically embedded in our environment. So we can also then look at the change in copper production globally over that same time period. So here what we're looking at is a graph. On the left is 1900, and on the right is 2024. And the black line is the percent increase in copper production from mining operations relative to 1900. So if we take 1900 as our baseline year, in the year 2024 globally, we will produce or mine or consume about 4,500% more copper this year than we did in 1900. And if we look at it on a per capita basis, in the United States, we consume about 12 kilograms of copper per year in everything, our built environment, all of the technology that we consume. The European Union is about 8.4 kilograms of copper per year, and the rest of the world is 3.2 kilograms. So now if we start to think about global development, there's a lot in the news on a regular basis about equitable global development, the United Nations Sustainable Development Goals, and the UN Sustainable Development Goals. Among those goals is access to clean and affordable energy, access to food, access to education, access to healthcare, medical care. So what we're talking about when we talk about global development is increasing the per capita copper consumption for the entire world to values that are current values for the European Union and the United States and other already developed countries. So now we can look at world population in the gray and compare it to copper consumption in black. And all I want to highlight here is that over the last 125 years, what we see is world population has increased from about 1.5 billion to 8 billion. And copper consumption, millions of tons per year, has also increased. And global development requires that copper consumption continue to increase. So if we look at world copper consumption per capita or per person from 1995 projected out to 2050, what we can look at is, data for China. So in red, we're looking at the real measured copper consumption per person from the early 1990s through today, and then projected out over the next several decades. We can look at Vietnam, a country that is rapidly developing, and we can look at historical and projected copper consumption per person. We can look at Mexico, and we can look at India. And if we were to only focus here on China and India have roughly equal populations at about 1.5 billion people. And if equitable global development means that everybody in India has access to the same amount of energy as every person in China has access to, then this requires, in order for India to move up, India's consumption of copper has to increase significantly. So ignore most of the stuff on here, and I just want to highlight the row on the bottom. Current in-stock copper use in the United States is 238 kilograms per person. In order for India to have the same level of infrastructure as the United States does today, requires 354 million tons of copper. In order for Nigeria to have access to the same infrastructure as the United States today, requires 114 million tons of copper by the end of this century. And similarly, for the DRC, for infrastructure in the DRC to be equal to the United States per person by 2100 requires 95 million tons of copper. If we sum this globally, what we need globally is about 2 billion with a B, 2 billion tons of copper to build equitable global infrastructure. There's a lot in the news about access to electricity, and most of what you read and what you hear, in my opinion, gets it wrong. So when people talk about having access to electricity, the way that we determine that is by measuring the number of people that have enough electricity over one 24-hour day to light a light bulb for 4 hours and charge a smartphone twice per day. That's radically different than the amount of electricity consumed in the United States and the European Union. We hear a lot about AI. AI uses a lot more electricity than non-AI computations. So training a large language model such as ChatGPT, that uses about 1,300 megawatt hours of electricity, which is equal to sitting on your couch and watching Netflix for 185 years without taking a bathroom break. Phenomenal amount of electricity. Similarly, we hear about mining Bitcoin. Right now, the same amount of electricity is being used to mine Bitcoin as the whole country of Bangladesh. And if we look at data centers globally, if we were to rank data centers as their own country, they would rank as the 17th largest consumer of electricity in the entire world, more than 176 countries. So data centers as a country use more electricity than each of these other countries here listed on the right. And by 2034, the amount of energy, electricity used by data centers will be the same as the total amount of electricity used by India. So when we talk about equitable global development, we're talking about increasing energy consumption for everyone around the world, and simultaneously, we're increasing the energy that's consumed by data centers and AI and Bitcoin mining and other technologies. So a question is, do we have enough copper to make all this happen? So if we look at how much copper we need globally in order to maintain what we would think of as normal economic growth, we can look at how much copper we have mined in the past. So here we're looking at on the y-axis is copper demand for normal economic growth. So here in red is the data plotted from 2010 through roughly today. And this is the amount of copper that was mined globally and used by society. In 2018, it was 20.4 million tons of copper. In 2024, it'll probably be about 22 million tons of copper. And if we project out to 2050, sort of normal business as usual economic growth, then it means annual consumption roughly doubles. So over the next 30 to 40 years, we need about double the amount of copper to be mined every year as we have in the past. In the United States and the European Union and Canada and China and every other country on the planet, there's a lot in the news about carbon neutrality. And almost every country around the world has pledged to become carbon neutral by 2050 or by 2060. And the reason behind carbon neutrality is to try and eliminate the impacts of using fossil fuels as our primary energy source. So globally, coal plus oil plus natural gas are about 85% of primary energy consumption. Everything else, solar, wind, hydro, nuclear, modern biofuels, everything else is 15%. And we know that combustion of fossil fuels irreversibly produces carbon dioxide, and we can demonstrate that the cause of rising CO2 emissions is the increasing combustion of fossil fuels. If we look at carbon dioxide emissions globally, energy production is about 75% of total carbon dioxide emissions. So when countries are pledging to become carbon neutral by 2050 or 2060 in the case of China, what they really are focused on is reducing the use of fossil fuels as our primary energy source. So in the United States, the European Union, China, Japan, Korea, other countries, there have been several proposed pathways that get us to carbon neutrality. One of them is electrify everything. So everything that we use is electric. We drive electric cars. All of the electricity for our cars come from solar panels and wind turbines. All of our cooking is done by conduction, electricity. All of our air conditioning and heating is done with electricity. All of our hot water is electric. And in order to make sure we have electricity when the wind isn't blowing and the sun isn't shining, we have massive amounts of grid scale battery storage so that everything we do plugs into an electric outlet. Now, electricity requires copper. So this is a simple example of copper being used to generate electricity. So in this video, what we're looking at is we've got strands of copper that surround a permanent magnet in the center. And the permanent magnet consists of neodymium and iron and boron. And if we spin a permanent magnet within a stationary copper frame, then an electric current is generated. And this is what we plug into when we charge our cell phone or we turn a light on. We're literally plugging into a system where on the other end is copper. So when we talk about electrify everything, the most important metal for this energy transition to electrify everything is copper. And I'll focus on the United States because the United States is 4% of global population, but we consume 17% of global energy. So in the United States, the map on the left, the blue dots show you where we have utility scale wind farms today, and the orange dots, which are not very many, show you where we have utility scale solar farms today. In order for the United States to become carbon neutral by electrifying everything using wind and solar, we need the map on the right. So the map on the right shows you in blue all of the utility scale wind farms that we need to build between now and 2050. And all of the orange shows you the utility scale solar farms we need to build between now and 2050, including lots of on-land wind and solar. And then off the east coast of the United States, lots of floating wind farms off of New York, Boston, parts of Maine, down here off coast of Florida and Texas. So to a geologist, when you look at a wind turbine, this is what you see. You see all of the natural resources that are required to build the wind turbines. All of the resources physically embedded in the wind turbine: molybdenum, zinc, copper, silicon, iron, neodymium, boron, dysprosium for the magnets. We need steel that holds the structure up. And then we need also phenomenal amounts of battery energy storage to store excess electricity that we can draw upon when the wind isn't blowing to produce electricity in real time. Similarly, when we look at solar panels, we see all of the elements that are required to physically manufacture solar panels. And for both wind and solar, copper is fundamental. When we look at electric vehicles, we also see all of the metals that are required to build battery electric vehicles. So we often talk about them as lithium-ion batteries, but every lithium-ion battery car requires about 8 times more copper than lithium, plus nickel, plus manganese, plus cobalt, plus rare earth metals. So a tremendous amount of resources in every vehicle. And globally, we have about 1.7 billion light-duty vehicles, and the forecast over the next 60 to 80 years is that the number of vehicles globally could increase by as much as double. So we could see somewhere on the order of 3 billion cars globally. So if all of those vehicles are battery electric, then it's a simple math calculation to take 80 kilograms of copper per vehicle times 3 billion vehicles over the next 100 years. We need a phenomenal amount of copper. So if we stick with just wind and solar, onshore, per megawatt capacity of wind generation, we need 5 tons of copper. So every time you see a wind turbine on dry land, like the ones in this picture, they're typically rated now at about 2 to 3 megawatts per turbine, which means every turbine has 10 to 15 tons of copper per one turbine. Offshore, it's double. So offshore, it's 10 tons of copper per megawatt capacity. And then solar is 5 tons per megawatt capacity. So a question is, a question is, can mine supply meet projected demand for electrification? So if carbon neutrality is achieved by a combination of wind energy, solar energy, battery electric vehicles, each of these, we know how much copper they require. Can we mine enough copper to actually meet demand? So let me look at demand first. So just to highlight what had that slide in there by accident a few minutes ago. So here's copper demand in red. So this is copper demand, which is equal to the total amount of copper mined globally from 2010 to 2018. And we can project from 2018 using historic increases to project out to 2050, which is when the United States wants to be carbon neutral, and then 2060 when China has said they'll become carbon neutral. And so just normal economic growth requires by 2050 mining about 36 million tons of copper in 2050 from about 22 million tons today. If you calculate how much copper is required for every car in the world to be a hybrid electric vehicle, we need by 2050 another 1 million tons of copper per year. If every car is a battery electric vehicle, then we need about 10 million tons more copper per year by 2050. If we upgrade the grid so we can charge all of our electric vehicles, then we need in the short term to see a bump in copper production. But similarly, by about 2050, we need about 44 million tons of copper that year. And if the whole world electrifies by a combination of solar plus wind plus battery electric vehicles to achieve net zero, then by 2050, in that year, we need to mine 90 million tons of copper in the year 2050. Now, these are the mathematical results of converting all of our existing energy infrastructure, eliminating natural gas, eliminating oil, eliminating coal, and only using wind electricity, solar electricity, battery electric vehicles, and also built into this green line is enough grid scale battery storage for about 28 days of battery backup with no wind and no sun. So we need to go from roughly 20 million tons of copper per year to about 90 million tons of copper per year in 2050. So what does that mean? Can we actually anticipate that mining companies can meet that demand? Well, globally, there are about 700 active copper mines shown here in the red dots. And among those 700 active copper mines, since 1900, this blue line is the annual mine production of copper summed over the entire world. So the y-axis here is global mine copper production in millions of tons per year. So what we did is we simply took this historic mine production from 1900 through roughly 2020, and then you can extrapolate that if mining companies in the future produce copper every year at the same rate of increase as they've done in the past, then the prediction is that by 2050, mining companies could produce 37 million tons of copper, mined copper. You can look also at the impact of recycling. So there's a lot in the news on a regular basis about a circular economy. So if you take historical recycling rates for copper and you assume that future recycling does not improve, the dotted line is how much copper we will produce from recycling copper, and the black line is how much copper will be produced if copper recycling increases or improves every year at the same rate of improvement in the past. And so the expectation then would be that in the year 2050, the total refinery production of copper, the total refinery output would be 50 million tons. So we'd have 37 million tons from mines and about 13 million tons from recycling copper. So recycled copper would be about 35% of global supply, and mined copper would be 65% of global supply. So what does that mean in terms of mines? So these are the top 10 copper producing mines in the world, listed in order from 1 to 10. The average copper mine, that decimal's off by 1. The average of the top 10 is 0.4719 million tons per year, or about 500,000 tons of copper per year. So if we take the copper demand that we need for the energy transition, and we frame it in terms of the number of mines that we need, just to satisfy baseline economic growth in red requires opening up 1.1 of these mines every year for 30 years. So every year for 30 years, we have to have a mine open that produces about 500,000 tons of copper per year. If the entire world drives an electric vehicle, we need 1.7 of these mines to open up every single year for 30 years. And if the whole world achieves carbon neutrality or net zero by 2050 by a combination of wind plus solar plus batteries plus electric vehicles, we need 6 of these mines to open up every single year for 30 years. And everyone listening knows that is not going to happen. And it's not going to happen for several reasons. Among them is shown in black here now in the center. This is the amount of copper that is already committed by operating mines and mines being constructed. So these are data from S&P Global for all mining companies globally that are currently operating copper producing mines and are constructing new copper mines. The anticipated production over the next decade will peak and decline. So there's a huge problem here. We need the red line for just normal economic growth. We need these black line and blue lines here for everyone to drive an electric vehicle. And we need the green line to achieve net zero by electrification with wind and solar and battery. And yet the black line tells us that copper output from mines is actually going to decrease over the next decade. This is a huge problem that policymakers do not seem to fully understand. So I know, Beatrice, I'm coming up on time, aren't I?
You good? You good to finish? Are you close?
Okay. Yeah, I'll finish here then. So
yeah, no worries. Take your time.
There's a huge disconnect between policymakers across all countries globally who have put in place policies to achieve carbon neutrality or net zero by 2050 or 2060. And the pathway to achieve carbon neutrality by electrification through solar and wind, it is not resource viable. It's just not. Because the lines that are shown here, these are the tonnages of copper required to electrify the global energy infrastructure. And the black line is how much copper all currently operating copper mines and mines being constructed, how much copper they will produce. And so one of the things that I suggest SEG and all of the members in SEG should do is really start to focus on communicating to the general public that we engage with, and certainly communicating to policymakers that you cannot build renewable energy infrastructure without the raw materials. The most important raw material is copper by far. One could argue iron because we need iron to make steel for infrastructure, scaffolding. But copper is the most fundamental metal for the energy transition. And over the next decade plus, the amount of copper that will be available for the energy transition will decline. And this also presents a huge problem for equitable global development, because in essence, what we set up is a competition. We've got high income, already developed countries that want to transition from combustion of fossil fuels to renewables. And we've got 6 billion people around the world in low income, lower middle, and upper middle income countries. India has 1.4 billion people. Nigeria is going to have 400 million people. The DRC is going to have at least 300 to 400 million people. So what we'll see is this competition between the high income countries that want copper for the energy transition and the lower middle, and upper middle income countries that want copper for human development. And if the copper is overwhelmingly allocated to the energy transition in high income countries, then that will result in the lack of human development for the rest of the world. And I'll stop there.
Thank you so much, Adam. That was great. I was about to mention your communication is so clear and so easy to understand, but many other people have said the same here in the chat. So thank you. Thank you so much for that. We have several questions for you. Let me start with, thank you for nice talk, Adam. And for I'm so sorry, it's the next one. Here, there we go. Let me just share my screen first so it's easier. Here, window, and there we go. All right, so we are about to start the question and answer session. Here again, we have the Q&A button on the top of the screen. So if you can you please and tap your questions in there, so it's easier for us to see your questions and to upvote questions. We have already one question in here in the Q&A and several other ones in the chat. I'll start with the one in the Q&A. How much less copper would be needed if the assumptions were based on, let's say, Switzerland level of energy consumption rather than exacerbated US level? How would you recommend discouraging having the US as a living standard? Nobody really needs 24 applicants and 2 cars.
I agree 100%. And Larry Cathles and Dan Wood and I are actually finishing a paper that we're going to hopefully publish in SEG Discovery next year. And if we were to take more realistic approaches to the energy transition, for example, if we used nuclear for baseload power and 90% of our electricity energy came from nuclear with 10% from wind, the amount of copper for that is just a little bit more than business as usual. So what is unrealistic is transitioning from combustion engines to solar and wind and battery electric vehicles. We need a lot less copper if we transition to nuclear and if we transition vehicles to hybrid vehicles, not fully battery electric vehicles.
Thank you. And the next one, stellar talk, Adam. You summed up all the data so succinctly into one clear hit-home talk. Has a calculation been made to estimate whether or not the near-surface minerable copper in the crust would actually be enough to meet the demands of our current population growth and electrification projections?
Yes. So several groups have done that. Larry Cathles and I published a paper this year, and our model predicts that there is about 6.5 billion tons of copper in the upper 2 kilometers of the Earth's crust. The USGS under Jane Hammerstrom published a huge report in 2017, 18, or 19. And Jane's group also published a total copper resource within the upper 2 kilometers. I think hers was somewhere closer to 5 billion tons of copper. So yes, at least based on those model estimates, there's more than enough copper at depths that are achievable with current mining technologies in order to develop the whole world.
Excellent, thank you. Has the UN proposed any global political initiatives to address the anticipated shortfall in future copper production?
Not that I am aware of.
Perfect.
No, I think the UN does a lot of great work. The policies, though, right now are disconnected from reality. So, for example, if you read the entire UN Sustainable Development Goals, there's not a mention for mining, not one. Not a single mention for the need to mine the resources to achieve the SDGs. So again, just a really big disconnect between policymakers and reality.
That's surprising for sure. Great presentation. Very important observation supported by lots of excellent data. Can you share the sources of data you use for creating your charts? Human development, energy use, copper consumption, etc. Thanks.
Yes, yeah. If anybody wants me to share it, they can send me an email. I'd be happy to share the presentation. And the sources of data were World Bank. For energy consumption, I compared data from the CIA. The U.S. federal government tracks energy consumption per year on a national and per capita basis. So that's where those data came from.
Thank you. Adam, what about substitutes for copper? PEX for plumbing, iron flow batteries for grid storage, etc.
Yep. So substitution, it has been important and it will continue to be important. And if we only look at the US as an example, and again, it's not the best example because we consume way more energy than we should. In the United States, we currently consume somewhere on the order of 12 kilograms of copper per year. So we have substituted, for example, aluminum has been used as a substitute for high voltage electricity transmission. That's been normal now for decades. We have increasingly substituted PVC and other types of plastic in plumbing. And even with those substitutions, the per capita copper consumption has continued to increase. I know in vehicles, there's a lot of ingenuity that's currently reducing the amount of copper that's needed, but it seems impossible to substitute away from using copper. And if you substitute something for copper, then that requires an increase in the mine production of that something.
Thank you. Regarding the urgent demand for copper, should the industry focus on improving extraction techniques for existing lower grade copper ores or invest more effort into discovering new high grade tier 1 copper deposits?
All of the above. I think the mining industry really needs young, agile. The mining industry really needs new ideas. So the mining industry, I think what we see when we look at copper over the last several decades, the number of tier 1 discoveries continues to decline year over year. Even though exploration budgets are now a factor of 5 higher than they were 15, 20, 25 years ago. So we're spending more money and we're finding less copper. And I think that's, and I don't think that's because there's less copper to discover. I think we need to develop new technologies to look into the earth to make new discoveries. And then I also think, and we see a lot of this happening already, mining companies are looking at ways to recover copper from lower grade deposits. And this is something that mining companies do really well, and they've done it for a long time. You know, if you go back to the 1600s and 1700s, the average grade of copper deposits that were being mined was like 5%. And something less than 5% was not economic. Now we're mining deposits at 0.3, 0.4%, and they're economic. And I think that mining companies will continue to improve the ability to mine copper at grades of 0.2, 0.1, 0.05. It's just research and development that has to happen along with high copper prices. That's something that's really important.
Thanks. And the last one, great presentation, Adam. Do you see deep sea mining as a potential solution to this copper and critical metals challenge?
Yes, but we don't need it. So I think that there is more than enough copper on dry land to mine to meet supply, to meet demand. But if mining companies continue to be denied permits to build new mines, then ocean mining is inevitable.
Thank you. Thank you so much. So that was great. Thank you for being here. Thanks for joining us for the excellent talk. No worries. Thank you. There's several compliments for you in the chat. I'm sure you got a chance to read them later, several other questions. So feel free to take your time, type them in, answer the questions. Your email has already been shared with the folks in here.
Yeah, I was just going to show one more thing for any of the students online. Steve and I wrote this book a few years ago, and it's now available for free. So if any of the students want to take grab the QR code here, you can download this book for free now.
Oh, amazing. You are projecting the QR code, right?
Yeah, am I? Do you see it?
I don't see it, but maybe that's because I'm sharing. Let me stop sharing.
Oh, yep. Hold on. All right, if you're, let me do it now.
Yes, we see it. Excellent. here. All right, it's hanging there for a few minutes before, a few seconds.
All right, you think we're good?
I think we're good. Yeah. I'm sure someone already took a screenshot and is sharing it with everybody already. So
Good.
you're good.
Thanks,
Thank you
Piercey.
so much for your accessible language and for
Thank you
amazing
very
talk.
much.
Thank you. So I'm sharing my screen again. Just a sec. So moving on, we have here some comments from Ann Thompson from Petra Science Consultants Inc. So Ann is the SEG president-elect for 2024. And Ann is the producer and co-host of the Discovery to Recover podcast and recent author of Innovation in Mineral Exploration, published by PDAC. She has 35 years experience working in and consulting to the mineral exploration industry, including fieldwork and applied mineralogy. She was an early adopter of field spectroscopy and co-edited the Atlas of Alteration, a resource for exploration geologists. And in his company, Petra Science, a partnership with John Thompson, focuses on technology, sustainability, and innovation in the mining industry. Anne was named the Women in Mining UK Global 100 Inspirational Women in Mining in 2020. And we're honored to have you here. Feel free to come up on screen. I heard you have a video for us.
I have the video. I can go ahead.
I'm here, but I think you're just going to play the video, right? Because my internet is just not so good.
No worries with that.
Okay. Yeah, great
We'll
to
take care
have
of it.
everybody here. Thank you.
Thank you, Anne.
I'll go ahead and share my screen, Beatrice. But thank you.
For the Traveling Lecturers webinar. It was a fantastic event. Thank you to all the staff and the volunteers who've worked hard to make this event possible. It's always harder than it seems to do a virtual event, but it's been great to be able to share it with such a large audience around the world. I also want to take a moment to introduce myself. I'm Ann Thompson. I'll be president in 2025 and very excited and honored to have that position following a cast of extremely impressive people. So a little daunting, but I know that the council and other people, volunteers and staff around me are all fantastic. And so I feel like working together, we'll be able to accomplish some things. So just to let you know what I'm thinking in my three big main things that are foremost, which is we're looking at having some more increasing smaller conferences or meetings that might occur regionally in different parts of the world, might be topic focused, hopefully with a field component and or possibly a lab component, hands-on effort. That's a new idea that hasn't really been in SEG much, but we'd like to try and make that happen. Also, conference accessibility and accessibility in general for SEG to make it affordable for more people to be a member. That's a huge goal, and it was very successful in Windhoek. We'll continue for Brisbane and the conference, and then step by step try and build this out to be something that is a larger program that provides greater access to our organization globally. We're working with partners and sponsors on that, and like I say, it's a work in progress, but we want to make sure we get it right. Governance, not very glamorous, but we are definitely in need of modernizing our bylaws, increasing our transparency, making sure our processes are clear. And that's a big job. So I'm taking that on in 2025, and undoubtedly it will take more than a year to finish, but we will get it going and work towards that goal. But as part of all this, remember that our students are huge. This is a big part of what SEG does. We're a global force of student chapters. They're all over the world, but very excited to welcome more chapters in Southern Africa, and really looking forward to continued interaction in Africa and growth of membership, and hoping that we can achieve some of the same results in Australia next year as we increase engagement and are able to meet in person. Discovery to Recovery. I have to talk about podcasts, right? Because I am host and producer of Discovery to Recovery, along with my team of presenters, and I'm always looking for new presenters as well and hosts. We have over 50 episodes out and over 90,000 downloads, so we're hugely successful. A new season is coming, season 5, so we look forward to that. Just a little bit slower than usual to get it off the ground, but it's coming. And the Student Podcast Challenge is on again this year. We had 18 entries last year. I'm hoping for more this time. And yes, the top few entries will be streaming soon on Discovery to Recovery. So thank you everyone for your involvement in that and your support of it. Give us a good review. Give us some more likes on social media, always appreciated. And Brisbane, well, it's already been mentioned, I'm sure, tonight at this event, but I'm really excited because I started my field exploration career in Brisbane many years ago. Spent a couple of years living there. This is the venue, looking across at the venue. So we're going to have fun, but we're also going to have a fantastic technical program that's being worked on by Rick Valenta and Mark Napa at UQ. They're leading the charge, and it's going to be a very, very good event and very exciting. So hope to see you there. As the year closes, I want to thank our outgoing council members. Stuart Simmons is a rock star, has set us up for success, navigated us through a very tough time, and can't thank him enough. Simon Jowett, VP Student Affairs, who's spent years dedicated work in that role and done a huge amount for SEG. We mostly appreciate you. And our outgoing council members, Xiaosheng Chang, Mary Little, and Cesar Vidal. Thank you very much. And I hope we also see you around again. I'm sure we will. Incoming council members, Alan Wilson is our new president, so he'll be president in 2026. Leijun Zhang will be VP Student Affairs, and our new counselors, Lynette Grayling, Rowena Duckworth, Patrick Redmond. Thank you for stepping up to the plate, and I look forward to working with all of you. And mostly, thank you to everybody. Thank you to everybody who's a member of SEG. Thank you to everybody who reads the journal, who picks up Discovery, who likes a post on LinkedIn. Thank you hugely to the unrecognized reviewers for the journal, for the people who write articles for Discovery, for the mentors, for the lecturers, for anybody who goes out and gives a lecture, and we probably don't even know you're doing it, but you're all part of the SEG community, and you're all really vital to our success and to our connectivity around the world. I also really want to note how important it is that we continue to build our community and to continue to connect with each other. We have aspirations, we have things we want to do, and in order to do that, we're going to have to continue to build our financial resources. We have a very awesome foundation, and we have the money and the ability to do a lot of things. But if we want to increase, if we want to do anything that's pushing out our boundaries, that's creating more opportunities, that's building out field programs, we will have to increase our financial base. And the way we've done it to date is amazing because members are a vital part of that. And we have continued to build slowly and carefully with individual donations. And that has to continue because it is so important to us being able to succeed for decades to come. If we want to do open access, if we want to be more accessible, all of these things are going to require financial resources. And our partners, our industry, have also been a huge part of our success and will continue to be as we move forward, and we'll continue to work with them and talk with them to make sure that we are all working in the same direction together. So thank you, everyone. Thank you for your participation. Thank you for everything you do. And it's the giving season, so do think about it. If you feel like you can, we will much appreciate it. And lastly, all the best for the holiday season. I put this up at Champagne Pool. It's in honor of Stuart Simmons. A few bubbles never hurt. And so we wish you the best for an exciting and great 2025. Yes, may it be full of bubbles. Thank you.
That video was such a great idea. I'll keep that in mind when I predict bad internet connection in the future. Thank you, Anne. That was an amazing video. Thank you for that. Thanks for your efforts. And I know I speak for lots of women when I say we look up to you as we look up to Sarah and to Moira, to your achievements. It's very inspirational for us just starting out our careers. So thanks for everything you have done. And best of luck in 2025. We are definitely very excited about that. And now I think we are ready to wrap up. I'm going to share my screen again just to show you some last slides in here. I guess you're seeing that already. So this one, just to share with you guys some upcoming instructional events that we are about to have. We have a 2-day course about induced polarization for geologists. Oh, done. Coming again. Yeah, here, there we go. Induced polarization for geologists. It's a 2-day course that's going to happen in January. Then we have another 2-day course about orogenic gold in Africa. I'm doing that. Yes, it's good. And orogenic gold in Africa and worldwide in February. And then a virtual course, drill, deal, or drop, exploration decision making through commodity and project cycles. Then we have a 1-day course, ancient and modern volcano-hosted massive sulfide deposits in February, and another 1-day course, ore deposits at nanoscale. Here. And there you go. Just to complement, just to add another information to Anne's video for you, your podcast lovers, don't forget to check out the incredible stories that we have there, as Anne said. And student chapters should note the competition is open. It's moving by itself. I'm so sorry about that. Yeah. So the competition is once again open. And so SEG student chapters are all invited to produce a 12-minute video, a 12-minute audio podcast. Sorry, it's an audio for about the world of ore deposits. And as a personal comment, I would highly recommend student chapters to do it. Last year, we participated, we produced our video. We didn't win the prize, but the process was so much fun. We are definitely considering doing that again this year because it's a lot of fun. It's so nice hearing the stories and sharing it. And there's a prize, which is a plus. So there's a chance for student chapters to win thousands of dollars in prizes and maybe be featured in an episode of Discovery to Recovery podcast. So moving on in here, we also would like to bring your attention to that the SEG News compilation about mineral deposits of Africa, Foundation for Future Exploration, is now available for purchase, showcasing Africa's rich mineral resources, including near 500 papers on iconic deposits and recent discoveries in Africa that have been sourced from over a century of economic geology and other SEG publications. So this comprehensive update by Bob Foster of the 2016 compilation is available now on the SEG store, and the price for members are $99 American. And here Another reminder, but Ian already mentioned it. So the conference will be held in Brisbane, and we are very much looking forward to that. So hope we'll see you there. And thanks again. Thanks so much for attending the conference, to being here with us. We are aware it's very late for many of you and in many different countries, so your attendance is very much appreciated. Thank you. Thank you to the attendees. Thank you for the presenters, for the folks in the background that were helping me here during the whole process. Thank you so much for that. And also thanks a lot for our members out there. As I said before, it's going to be available. We are recording this. It's all going to go to our YouTube channel as well as the SEG website. So please keep an eye on that. Thank you so much.